Hi everyone. So let's start now. This is our final lecture of pipeline. In this lecture, we will study control hazards. Okay. So this concept we need to see control dependency and control hazards. So that this concept, this is our final concept. Everything else we have seen. We will also see structural hazards. Okay. So data hazards we have already seen. Difference between data dependency and data hazard, that also we have seen. And in this lecture, we will see structural hazard and control hazard. Okay. So this is our final lecture of pipeline. We will see many gate questions. We will solve many gate questions also. So let's start now. Before we start, please tell me, are you confident in data hazards and data dependency? In All India Mock Test 3, I put one question of data hazard. Did you solve it? There was one question in which I was asking number of WAW hazards, number of WAR hazards, number of RAW hazards. Okay. So that question, did you solve? Okay. I think that question has become easy after these lectures, right? Okay. After our lectures, we have seen data hazards, data dependency, okay, all the concepts that are there: in order pipeline, out of order pipeline, in order execution, out of order execution. Okay, so everything we have seen. Now this is our final lecture. In this lecture we will study control hazards, control dependency, and also structural hazard. Okay, and then we will see all the gate questions which are from control hazards. Okay, so this will be a small class. Comparatively, this will be a small class. Okay, now let's start directly with structural hazard. This is a very simple topic. The name is structural hazard, or you can say resource hazard. Okay, this type of hazard is created because of lack of resources. Okay, so these are called I can say resource hazards, or I can say structural hazard. What is this? This is very simple. This is saying that, let me assume you tell me a simple point. You tell me, if you have lack of hardware. Okay, because of lack of hardware, let me assume you have a single memory. Okay, let's assume you have a two-stage pipeline. Okay, so let me give you example, or no, our usual five-stage pipeline. Okay, our classical RISC pipeline. Let's take our classical RISC five-stage pipeline. Okay, let's take that pipeline. But in that pipeline, let me for example assume, so you have a five-stage pipeline you have, and in that five-stage pipeline, let me assume that you have a single port on memory. Okay, so I can say that you have a single memory for instructions and data. Let me assume that you have a single memory, or I can say single port memory. Means basically what it means, you have a single memory for instruction and for data. Okay, you do not have instruction memory separate and data memory separate. Okay, you do not have one port for instruction memory, another port for data memory. You do not have that. Let me assume for a moment, that my computer is very cheap. Okay, so because of cost cutting, I only have a single memory for instruction and data. I do not have separate memory. Okay, in the same memory I have all my data, all my instructions. Now you tell me, if you have this type of situation, that you have instruction I1, which is a load word instruction. You are loading something from the memory. Let's assume in the register R1 you are loading something from memory. Okay, from memory you are loading something. So what this instruction means, can you tell me what this instruction means? This instruction means that in R1 we are loading something from data memory, from the memory, or I can say from data memory. This is the address, right? This we have already seen. What is this? This is your address. This is your memory address, correct? Okay, so this 2 plus R2, this is your memory address. Now what you are doing on this memory address, there is something, and that you are loading, that data you are loading into R1. Okay, so this is your memory address. You go to that memory location. There you have data, some value you have, that value you put in R1. This is what this instruction is doing. Now let me assume that you have some more instructions. You have I1 instruction, I2 instruction, I3 instruction, I4 instruction, and so on. They can be any instructions, I don't care. There are some instructions, I1, I2, and so on. Now you tell me, if you have a five-stage pipeline, now in this five-stage pipeline, what you have? So let's see the execution. Okay, now let me tell you the execution. So you can also do this, you can also try this on your copy pen. So this is your cycle C1, this is the cycle C1, then C2, then C3, then C4, then C5, C6, and so on. Now you can notice the instruction I1, which is a load instruction. This is your instruction I1. You are fetching it, then you are decoding it. In the you will also read the register. Tell me which register we are reading in this instruction. Which register we are reading? Tell me in this instruction, in this load instruction, which register we are reading? We will read which register? R2. Okay, we will read R2 because that is the register we need. We will read. Okay, so this instruction I1, this load word instruction, you are fetching. In the second clock cycle, you are decoding, you are finding what instruction this is, and also you are reading the source register. This source register you are reading. Then you are going to execution phase. In the execution phase, you will compute this address, this memory address you are computing in the execution phase. Then you are going to the date. Then you are again memory accessing, right? You are accessing the memory. So then you will access this memory, you will access, and then that value you will put in the register. So you will do the register write back. Okay, now then what you can do, this instruction I2, when you are decoding in the second cycle, when you are decoding, then instruction fetch, this hardware is free, right? Okay, this hardware, this stage is free, so you can fetch the instruction I2. When this instruction in the cycle C3, when this load instruction is calculating the address, okay, this load instruction is executing in the ALU, then what you can do, this instruction I2 can use the ID stage, decoding stage it can use, so it can use this, okay, and so on. So you can notice then it will go to, then it will in the cycle C4, instruction I2 will go to the execution stage, then it will go to the memory access stage, then it will go to the WB stage, register write back. Let's look at instruction I3. You can notice again that in the cycle 3, you can see which stage is free. Instruction fetch, this hardware is free, right? Okay, this fetching, this instruction fetch hardware, this stage is free, so you can fetch another instruction. This hardware can fetch another instruction. Then in the next cycle, the decode stage is free, so you can decode and you can read the source register. Then you can go to the execution stage, and so on, okay, and so on. Now let's see this interesting part. This is the interesting part. You tell me one thing, you tell me a simple point, you tell me this, in this stage we are accessing the memory, right? Yes or no? Do you agree with me that in which stage we access the main memory? Can you tell me? There are total 5 stages. In which stage do we access the main memory? Do we access the main memory in which stage? In the IF and MA, right? Let me connect my laptop to charger. You think about it. These are the five stages. In which stages, okay, there can be multiple stages. In which stages we access the main memory? Remember, there is a single main memory. Please understand, there is a single main memory for instruction and data. For instruction and data, you have a single main memory. There is a single port memory for instruction and data. You do not have separate memory. Now you tell me, there are 5 stages. Which stages? Okay, there can be multiple stages. Which stages use the memory? Which stages need to access the main memory? You tell me. Okay, so the answer is instruction fetch and main memory, right? Okay, so you can notice that if you have a single main memory, just think about it. If you have a single port memory, or I can say if you have a single main memory, okay, if you have a single memory, if you have a single main memory, then in that case, these stages, IF stage, because you need to instruction fetch. In this stage, you need to instruction fetch. Okay, so this stage will also need the main memory. It will also access the main memory, and this main memory access. Okay, so here you will data read, data memory read. Correct? Do you agree that if you have a single main memory for instruction and data, if you have single memory in which you have instruction also, in which you have data also, then you tell me these stages are using the same resource, yes or no? These two stages, okay, they basically access same resource. What is that resource? They access same resource. What is that resource? That resource is memory. Okay, so they access the same resource, right? Yes or no? Is this clear? Is this point clear? In this stage you are fetching the instruction, in this stage you are reading the data, but because you have a single main memory, because you have a single port memory, there is no separation between instruction memory and data memory. You do not have any separation. You do not have two memory, one for instruction, one for data. You do not have that. You have a single memory for instruction and data. Then in this situation you can notice that this is hardware and this hardware, both of these stages, they access the same resource. They are accessing the same resource, and that resource is memory. But they cannot do only one person can access, right? Yes or no? Is this clear? Only one person can access at any point of time. Only one person can access. Okay, if you have a single resource, you have a single resource, that single resource only one person at a time can access. Okay, so in this situation what will happen? In this situation this will happen that this load is using the memory, right? This load is already accessing the memory, correct? Okay, you are accessing the memory, you are accessing this memory resource, you are accessing. Okay, so tell me, can I do this instruction fetch? Sorry, so you can notice this will be like if id ex m and so on. Okay, so tell me now you tell me, can I do this instruction fetch? Can I do this instruction fetch? Can I fetch this instruction in this cycle? In the cycle C4, can I fetch another instruction? Can I do that? Tell me. In the cycle C4, can I fetch another instruction? Can I fetch a new instruction in this cycle? Because you can notice in this cycle C4, this load is accessing the memory, and this I4 also needs the memory. Both of them need to access the memory. Are yes or no? You have a single memory, you have a single resource. In the cycle C4, load is already accessing the memory. He needs to access the memory. Okay. In the same cycle, I4 also needs to access the memory. If you want to fetch, then you need to access the memory. So can you fetch instruction I4? And the answer is no. Okay, this cannot happen. This cannot happen. If this cannot happen, then what will happen? Then in this cycle, instruction fetch will be idle. Yes or no? In the cycle C4, you cannot fetch new instruction. So you can notice that in cycle C4, we cannot fetch new instruction. That is stall, right? We cannot fetch new instruction. That is bubble. That is stall. Okay. Is this clear? You cannot do work. Like you are idle. Your instruction fetch hardware. This is idle. Okay. So there is a bubble in the cycle. There is a stall in the cycle. Because what is ideal situation? Tell me. What is the most beautiful, most ideal situation? Ideal situation means in every cycle, one instruction you are fetching, right? In every cycle, new instruction you are fetching. In every cycle, new instruction you are fetching. That is the most ideal situation. But here you can notice that in the cycle C4, you cannot fetch instruction I4. So there is a bubble in the cycle. Okay, there is a bubble in the pipeline. There is a stall. So this is your structural hazard. This is called structural hazard, or you can say resource hazard. So you can read the definition of structural hazard or resource hazard. The definition is very simple, that a resource hazard occurs. This will occur when two or more instructions which are already in the pipeline, they are accessing the same resource. Is this clear? Read the definition and tell me, is this clear? Resource hazard, what it means? It means that it will occur. Remember, it will occur when two or more instructions which are already in the pipeline, they are already in the pipeline. Okay. And they need the same, sorry, you can notice it is not necessary, like basically you cannot fetch the new instruction. The point is very simple, that two or more instructions, they are needing the same resource. Okay. two or more instructions, they are needing the same resource. So because of this situation, because of this conflict, you can say that this stall can occur. This is called structural hazard. Please tell me, is this point clear? So you can easily notice this. You can focus on this. So you can see this is a load instruction. Just look at this example. This is a load instruction. So in the cycle C4, it needs to access the data memory. We need to access the data memory. This load instruction needs to access the data memory. In the same cycle, this instruction also needs to access the main memory, right? Yes or no? This instruction also needs to access the main memory. The structural hazard, what it says that we cannot load data and fetch instruction during the cycle C4. Basically, two things we cannot do together. You cannot, this and this, both of them cannot use the memory together. One of them can do that. Okay, so that is the reason. What is the solution? Okay, so you can notice same memory used. This is the reason this structural hazard is happening. This is happening because you are using the same memory for instruction and data. Same memory. So that is the reason. Tell me, what is the solution then? What is the solution? What is the solution of structural hazards? Can you tell me? Can anyone tell me what are the solutions of structural hazards? Additional hardware. Put additional hardware. That's it. Put additional hardware, right? Very simple. Very simple, that put additional hardware. If you cannot put additional hardware, because if you put additional hardware, then the cost will increase. Okay. The cost is going to increase. If you put additional hardware, then cost will increase. If you do not want to increase the cost, if you do not want to put the additional hardware, then what will happen? Then install. Clear? Is this clear to everyone? So either you put additional hardware, for example, separate memory for instruction and data, right? For example, separate memory for instruction and data. Okay, so you can notice either you put additional hardware, either you can do that. If you are rich, if you are very rich, you can do that. Okay, or the second solution will be what? Or the second solution will be install. So for example, if you do not put additional hardware, then you can put a bubble, right? Yes or no? Then this bubble will go through. Is this clear? Because in this cycle, you are not fetching any new instruction. In this cycle C4, look at this cycle C4. Look at this cycle C4 and tell me, in this cycle C4, you cannot fetch new instruction. In this cycle C4, we cannot fetch new instruction. So this bubble will go through the pipeline. This bubble is in the pipeline. And I told you in the last class, do you remember I told you that this bubble is simply your NOP instruction? This I told you in the last class, this bubble is basically your NOP instruction. So you can insert NOP instruction. This NOP instruction you can insert. So very simple. So you can notice these are the I can say either stall, bubble, NOP. Okay, this is your solution. Either you can do that, or you can put separate memory. Either this you can do that. Okay, this bubble basically, the reason is clear, right? Because in the cycle C4, you cannot bring new instruction. So in the cycle C4, this bubble will go in the pipeline. This bubble, this stall will happen. Very simple. In the next cycle, you can fetch. In the next cycle, you can fetch. Okay, very simple. Another solution is use instruction and data memory. This is another solution. Instruction memory, data memory. Very simple. Okay, so that's your structural hazard. Tell me, structural hazard, is that a very big problem? Is that incurable problem? This structural hazard, is that incurable? Is it incurable problem? This is not incurable problem. You can just put more hardware. Just put more hardware. That's it. This is the simple solution. This is very much curable. Okay, this is a curable problem. You can easily solvable problem. This is very easily you can resolve this. Very easily you can resolve this by putting more hardware. That's it. So this is not a big problem, right? This structural hazard, this is not a big problem, right? Agree? This is not a very big problem. That is the reason this data hazard and control hazard, We have seen in the last class data hazard. Is data hazard curable? Is data hazard curable? Tell me. Is data hazard curable? Is data hazard perfectly curable? Like, can I say it is 100% curable? Can I say this is 100% curable, resolvable? Or I can say avoidable. Is data hazard 100% avoidable? Tell me. Means the stalls by due to data hazard, are they 100% avoidable? The answer is no. See, WAW you can avoid. WAW hazard, okay, WAR hazard. These you can 100% avoid. These you can 100% eliminatable, right? In the last class, we have already seen this. What was the solution? These are 100% eliminatable. What was the solution? Renaming. Register renaming. Just don't use the same register again and again. Use the different register. Every time use different register. Whenever you are writing something, okay, some new calculation, whenever you are writing, then use a different register. So very simple. SSA, single static assignment, similar like that. So you can notice these two hazards, they are 100% eliminatable by register renaming. By this register renaming technique, means do not use the same register. Okay, means that is your SSA, single static assignment. Static single assignment technique, similar to that. Correct? Okay, static single assignment technique, similar to that. So these you can eliminate. But what about RAW hazards? What about RAW hazards? You can minimize them using forwarding. They are minimizable, like you can minimize them, but you cannot perfectly eliminate them. Minimization possible. Can minimize using what? Using forwarding. Using forwarding, we can minimize them. Using forwarding, we can minimize them. Okay. But remember, they are not 100% eliminatable. Okay. Remember, they are not 100% eliminatable. Is this clear? Whatever technique you apply, eliminatable. Whatever technique you apply, forwarding you apply, forwarding is not a perfect technique. Do you remember the example? Do you remember, for example, if you have load word R1, in R you are loading something. In R you are loading something. And let's assume that this R you are reading here. Okay. So let me assume that you have this type of situation. This is a load instruction. This is a RAW hazard. This is RAW hazard. And you can notice that even forwarding also cannot eliminate it. Even with forwarding, even with complete full forwarding, we need one stall. Okay, one stall will be there. One stall will be there. This we have already seen in the last class, right? Yes or no? Do you remember? Do you remember this? We have already seen in the last class that even with full forwarding, even if you have full forwarding, one stall will be there. Whenever this load instruction is there. Okay, whenever this load instruction is there. Because of the problem is this load instruction. Because data will be available in which stage? This correct value will be available in which stage? This correct value will be available in which stage? Stage 4, MA stage. Very good. End of memory stage, MA, memory access, data memory access stage. End of memory stage. Okay, so that is the reason. Even with full forwarding, even if you have full forwarding, you cannot eliminate. So is this clear? That RAW hazard, they are not 100% eliminatable. They are the real problem. They are the real problem. Okay. But structural hazard is not a big problem. This structural hazard, you can just put additional hardware. So you can 100% eliminate them. Okay. Eliminatable. So these are 100% eliminatable. Just put additional hardware. You can put more and more hardware. Okay. Whenever you are having any problem, just put more hardware. This you can resolve. So this is not a big problem. This structural hazard, not a very big problem. Okay, now let's see the next solution, that is control hazards. So far, who is the real problem? Like so far, who is the real villain? So far, who is the most dangerous villain? Like that is row hazard, right? So far, this RAW hazard. So far, this RAW hazard, this is basically, okay, not perfectly, I can say, not 100% eliminatable, I can say, right? Okay, not 100% eliminatable. Like there is no technique using which we can eliminate them 100%. Like we do not even have to worry about it. This RAW hazard, we do not have to worry about it. This is not possible. So this is the real villain so far. So far, this is the real villain in the pipeline. In pipeline so far. Now the next villain is coming. Okay. Now who is coming? Now the next villain is coming. This is the real villain so far. But now who will come? Now next real villain. Now next real villain of pipeline. By real villain, what I mean? Means these are not 100% eliminatable. Now the next real villain in the pipeline, who will come? And that is your control hazards. We will see that they also, you can minimize them, but they also not perfectly eliminatable. These are real villain. Again, you will see that again, these are not 100% eliminatable. You cannot eliminate them 100%. We will see that, don't worry. Okay, but you can minimize them. We will see the techniques. Now let's see the concept of control hazards. Structural hazard is clear to everyone. What is structural hazard? In the GATE exam, from structural hazard, some theoretical question can come. Actually, there is no question so far. In the GATE exam, so far, there is no question from structural hazard. If a question will come, some theoretical question can come. True, false question can come. Okay. So that was your structural hazard. Structural hazard happens when it happens when two instructions in the same cycle access the same resource. Is this clear? When structural hazard will happen, tell me. When structural hazard, when resource hazard will happen? When two or more instructions in the same cycle access the same resource. Okay, then the problem will happen. That is your structural resource hazard. Okay, now the next problem, that is control hazard. Now let's see. This is actually very intuitive problem, and the solutions are also very intuitive. So please try to understand this. Okay, very intuitive. Let's take example. Let me assume you have a two-stage pipeline. Let's start with two-stage pipeline. Assume that you have a two-stage pipeline. In this two-stage pipeline, what you have? There is stage one, in which you have instruction fetch. In this stage, you do the instruction fetch, and in this stage, you just execute. Basically, everything else you do in this stage. Is this clear? Okay. Here you fetch the instruction. Here we do the fetch, instruction fetch. Here we fetch the instruction. And here we do everything else. Here we do everything else. So let's assume that you have two stages. These are the two stages. You have a two-stage pipeline. Now, in this two-stage pipeline, let's assume that you have this sequence. There is a branch instruction I1, and this I1 is a branch instruction. This is a normal instruction. Let's assume this is some additional instruction. This I2, let's assume this is your some branch instruction. This I3 is another normal instruction. Another normal instruction, some normal instruction, maybe multiplication. Okay. Let me assume that this branch will go to IK. Let me assume that this will go to IK. Like maybe this can be a jump instruction. Maybe this can be a jump to IK. Okay. Is this clear? So jump to IK. You have to jump to IK. This is your instruction I1, I2, I3. Now you tell me a simple point. You tell me a very simple question. I'm asking, very intuitive. This is a very intuitive concept. So you have instruction I1, I2. I2 is a branch instruction. This instruction, this jump instruction, this is called branch instruction. Okay, conditional, so tell me, is this conditional or unconditional? This conditional or unconditional? This is unconditional. There is no condition. It will always jump. There is no condition, right? We do not have to check any condition. This is unconditional. We do not have to check any condition. It will always jump to, whenever you will go to I2, you are going to I2, then it will definitely go to IK. That is your unconditional jump, unconditional branch. Okay, now you tell me. So a simple question, let's assume this is cycle C1, then cycle C2, then cycle C3, cycle C4, cycle C5, and so on. This instruction I1, this is a normal instruction. Okay, this is a normal instruction. This is some addition instruction. You are fetching it, you are executing it. Okay, then instruction I2, you are fetching it, there is no problem, you are executing it. Okay, and remember this was your jump instruction. Remember this was your jump instruction. And instruction I3, tell me a simple point I'm asking. Tell me, when you are executing this, then what are we doing? Tell me one thing. In the instruction phase, can you find out is it jump or not? In the instruction phase, when you are fetching this instruction, can you find out is it jump or not? It is jump or not? No, you don't know. Yes or no? In this stage, when you are fetching this, you are fetching this from main memory to register. From main memory to CPU, you are fetching this. You don't know whether this is jump or not. So in this cycle, we don't know whether this I2 is jump or not. In this cycle, we will know. Maybe by the in this cycle, maybe by the middle, we will get to know. Yes or no? In this cycle, this is your cycle C3. Maybe at some point of time, we will get to know. This is your cycle C3. Maybe at some point, I don't know at which stage. Maybe at some point, we will get to know that, okay, this was jump instruction. At this point, let me assume that you get to know, we get to know, okay, we know at this stage, we get to know I2 is jump. I2 is jump IK. Okay, we get to know that, okay, it is a jump IK. It is a jump instruction which is jumping to IK. But by then, what would have happened? Tell me. By then, what would have happened? At this point, you are getting to know that I2 is a jump IK. It is a jump IK instruction. But by that time, this fetching would have started. The fetching would start here. In this cycle, look at this cycle. In this cycle, in the beginning, the fetching would have started. Is this clear? The instruction I3 fetching would have started. Correct or not? Is this clear? Tell me, is this point clear? That, okay, by this point of time, instruction fetching would have started. The instruction fetch hardware, this hardware would have started instruction fetching. Okay, so now there is a problem. What is the problem? Tell me. Now there is a problem. Actually, what should happen? This is what should happen, that after I2, you should go to IK. But there is a problem, right? After I2, you should go to IK. This is what is correct flow. What is correct flow? The correct flow is I1, then I2, then you should go to IK. But what is happening? In our two-stage pipeline, what is happening? Tell me. Please tell me. In our two-stage pipeline, what is happening? You are fetching I1, then you are fetching I2, then you are fetching I3, then you will fetch IK. Okay? Because now you know that you should fetch IK. So now you will fetch IK. Is this clear? In the cycle C3, you know that you should fetch IK. This instruction IK you should fetch. In the cycle C3, you know this. Okay, somewhere middle. In this cycle C3, somewhere middle, you know. Now you know. Oh, I should fetch IK. Okay, so now you will start fetching IK in the next cycle. In the next cycle, you will fetch IK. This IK you will fetch. This instruction IK you will fetch. Then this is wrong execution or not? Tell me. Is this wrong execution or not? Tell me this. This is wrong execution or not? This is wrong execution, right? So what should we do? What should we do? Tell me. In our two-stage pipeline, this is what you are doing. So this is like, from somewhere he has unwanted guest. So whenever in some marriage function unwanted guest comes, then what we will do then? Some unwanted person has come in a club, in a party, some unwanted person has come. Then what we will do that? We will flush it. Yes or no? We will flush it. So the solution, what is the solution? The solution is flush it. Flush means just remove it from the pipeline. Okay, what is the solution? The solution is solution. The name of the solution is flush. Flush it. This is the solution name. Flush it. Throw him. Okay. So what you will do then? So what you will do then? Then you will flush it. Okay. So when you know that, then you will flush it. It will not continue. So that is bubble has been created. Yes or no? So that bubble has been created. Agree or not? Because in the cycle C3, basically you are not, this bubble has been created. You will flush it. This is called flushing. A bubble has been created in your pipeline. Clear? Is this clear? That bubble has been created in the pipeline. So in the pipeline, there is a bubble now. Okay, so you can do like this. So now there is a bubble. In the pipeline, there is a bubble. In the pipeline, there is a bubble. That's it. Understood? Please tell me, understood? So you can notice this, you will flush. This instruction I3 has come. So you will flush. This will be flushed and this bubble has been created. In your pipeline, this instruction I3, you will flush it. It will be flushed. And because you are flushing it, so this bubble will be created. The bubble will be created. In the pipeline, this bubble will be created. Finally, you will fetch IK. This is the point. Okay, you tell me. So how many stalls? What is the number of stalls? Then tell me. What is the number of stalls then? What is the number of stalls because of this branch instruction? Because of this branch instruction, what is the number of instructions? What is the number of stalls? The number of stalls that you got, that is one. Number of stalls, only one stall you are getting. Only one bubble is going through the pipeline. Only one bubble was created. This bubble was created. Remember, only one bubble was created. That bubble is going. That bubble is going. Only one bubble was created. Only one bubble was created. That bubble is going in the pipeline. So tell me how many stalls you got? You got one stall. Why you got one stall? Because branch was resolved in the second stage. Is this clear? Why one stall? See, this is your I1 normal instruction. This is your I2, which was branch instruction. This was I3 and this was IK. This was IK. Now you tell me, in our two-stage pipeline, we got one stall, or I can say one bubble, due to branch instruction. Due to branch instruction, we got one bubble. Why? Why we got one only? Tell me why we got one? Because branch was resolved in the second stage. Yes or no? Branch was resolved. Branch target was resolved. Branch was resolved. Resolve means we got to know where to go. Yes or no? Because branch was resolved in second stage. In second stage, we found out where are we going. Yes or no? Is this clear? This branch was resolved in the second stage. Is this point clear? Because in the second stage, we are finding out where to go. In this second stage, this is your second stage. In this stage, you are finding out where are we going. In the execution stage, in this execution stage, you are finding out where are we going. That is called branch resolution. Branch resolution means you are finding out where to go. Okay, branch resolution. What that means? You are finding out where to go, which instruction to execute. Okay, so that is the point. So you are getting one bubble because in the second stage, you are resolving the, because you are in the second stage, we are resolving the branch. In the second stage, we are finding out where to go, which instruction to execute, which instruction to flush. All these things we are finding out in the second stage. That is the reason we are getting one bubble in the pipeline, because you are finding out everything in the second stage. So when you are finding out in the second stage, already one unwanted guest has come in your party. Clear? Visualization. Can you do the visualization? Please tell me. Just visualize. Because you are resolving the branch in the second stage. In the second stage, you are finding which instruction to execute, what should be the next instruction that should be executed. In the second stage, you are finding this. So by that time, one unwanted guest has already come in your party. Okay, so you should throw him. That is the reason, because you are resolving in the second stage. So one unwanted guest came in your party. Is this clear? One unwanted guest came in your party because you are resolving in the second stage. So if I resolve in the kth stage, then what will happen? If I resolve in the kth stage, then what will happen? If the branch target is resolved in the kth stage, if this branch target is resolved, is known, if the branch target is known, okay, this is called branch resolution. Branch target is known. This is called branch resolution. So you are resolving the branch, okay, branch resolve in kth branch resolve. So this is called branch resolve. Okay, means if branch target is known in kth stage, then how many unwanted guests will come in your party? In the kth stage, you will find out. Remember, in the kth stage, you are finding out in the kth stage. We are finding out what we are finding out in kth stage. We are finding the branch target. We are finding the branch target. Okay, we are finding the branch target. Then how many unwanted guests have come in your party? Then k-1 stalls. K-1, these many unwanted guests in your party. So there will be k-1 stalls in your pipeline. Let's move on. Let's take, so that is called branch penalty. This is called, these stalls are called, so these k-1 stalls, these stalls are called branch penalty. Okay, these k-stalls, k-1 stalls, these are called branch penalty. Okay, so because that is your penalty, that is the penalty you are paying. K-1 unwanted guest in your party. So these unwanted guests, these are the penalty. This is the penalty you are paying. K-1 stalls. This is called branch penalty. Let's move on. If you have 4-stage pipeline, and in the execution stage, if you are resolving, then what will happen? Let's assume you have a 4-stage pipeline. Just assume that now your pipeline is 4-stage pipeline. Okay, and your pipeline is like this: instruction fetch, instruction decode, execute, and let's assume write back. This is your pipeline. You have a 4-stage pipeline. Now you tell me, in this pipeline, if in the execute stage if branch resolve in execute stage, what it means? First of all, tell me what it means. Like, if branch resolve in execute stage, what it means? Just tell me this point. Branch resolve in execute stage, what it means? It means that in the execute stage, we are finding the target address. Okay, in execute stage, we find the target address, the target instruction. Okay, in this we find the target address of the instruction to be executed, of the next instruction that should be executed. That should be executed. Okay, so in this cycle, in this stage, we are finding which instruction, what is the next instruction that should be executed. Now you tell me, so if this happens, then what is the branch penalty? Let's find it out. If this happens, then what will be the branch penalty? If this stage, then this will happen. See, something like this will happen. If your instruction I1 is branch instruction, let's assume this is some jump instruction or some branch instruction. This is some branch instruction. Now you can notice that in your cycle C1, C2, C3, C4, C5, and so on. So when this I1, you are fetching it, the branch instruction you are fetching, at this point of time, you don't know it is branch instruction. Then you are decoding, you know that it is branch instruction. Okay, you know, in this decode stage, you know that it is branch instruction, right? Correct? Yes or no? I1 is a branch instruction. In the decoding stage, you know that this is a branch instruction, but what you don't know, you know this is branch instruction, but what you don't know where it is going. The target you don't know, yes or no? The target you don't know where it is going. It is a branch instruction that I know, but where it is going, that I don't know. Okay. Should it go to the next instruction, or should it jump? So we don't know. So that is the reason it will go to the execute stage, then it will write back. Now, in this stage, we are knowing. In this stage, we know the target address. The target address we will know in this stage. But at this point of time, who will have come in your pipeline? In your pipeline, 2 unwanted guests will come. Okay, 1 guest will come in here. Okay, and 1 guest will come here. So 2 unwanted guests will come, because in this stage, by the end of this stage, you are finding the target address. In this stage, you are calculating the target address, calculating the target address. So I can say at the end, you are calculating the target address by the end of this stage. Okay, so by that point of time, 2 unwanted guests have come in your party. Okay, now by chance, if you know that we will jump, then these should be flush. Yes or no? If you know by chance, for example, if this is your instruction jump IK, or maybe jump I10, then what we will do? Then these must be flush. We will flush them. And because you are flushing them, so how many bubbles are created? Tell me, how many bubbles are created? 1 bubble. Because you are flushing them, so 1 bubble and 1 bubble. So 2 bubbles created. So there are 2 stalls in pipeline. Okay, that is your branch penalty. So if you have a 4-stage pipeline, and in the execution stage you are resolving the branch, then what is the branch penalty? Tell me, then what is the branch penalty? Is it 2? The branch penalty will be 2. 2 unwanted guests will come to your party. Understood? So if branch resolves in execution stage, then branch penalty will be 2 stalls. I hope you understood this. Please tell me, did you clearly understand what is happening here? Did you understand it clearly? In the decode stage, if by chance we resolve, then what will happen? The same previous question, the same previous question, but in the decode stage, if we can somehow find the target address, tell me, then what will happen? The same previous pipeline, 4-stage pipeline, but in the decode stage, so you can notice, if the branch address is computed in the decode stage, then what will happen? Branch address, the target address, you are calculating in the decode stage, then what will happen? The same 4-stage pipeline, you have a 4-stage pipeline. Okay, you have a 4-stage pipeline. This is your jump IK. This is the jump IK. So you can notice that if you are in the decode stage, if you are finding where to go, then only one unwanted guest will come. This is the unwanted guest, then only 1 unwanted guest. Only 1 unwanted guest. So of course we will flush it. Of course, that unwanted guest we want to flush. We will flush it. This is the mechanism actually. The solution is flush. Just flush it. So if you flush, how many bubbles will be created? How many bubbles will be created? 1 bubble will be created. Okay, so what is the branch penalty? Now what is the branch penalty? That is only 1. Okay, branch penalty is 1. Very simple. This is the question. Okay, this is everything. This is your branch. This is your control hazards, control dependency. Now let me just explain one point. Basically, whenever there is a branch instruction, for example, if you have this instruction I3, if this is a branch instruction, okay, like if this is a branch instruction, branch not equal, BNE, branch not equal, if R1, R2, something like this. What this means? Tell me what this instruction means. This instruction means jump branch if not equal to some location ik. Okay, here you have some location ik. This is your some location ik. What this means? This actually means that branch if not equal. So when we will jump, it simply means that it means jump to ik if R1 not equal to R2. Are you getting my point? If R1 not equal to R2, because this means branch if not equal. This means branch if not equal. If they are not equal, then branch. Okay, jump if they are not equal. So you can notice this is your I3 instruction. Now this is your I4 instruction. Okay, then there are some instructions. Now you can notice that very simple point I'm telling you, you can notice that do we know these instructions to execute or do we know these instructions to execute? Do we know that when we are fetching this branch instruction, at that point, when you are fetching this instruction, at that point, do we know should we execute these people? Should we execute these people or should we execute these people? We don't know. So there is a dependency. We don't know either they will be executed, or these people will be executed. We don't know. So we can say that these people are control dependent on I3. Can I say these instructions, these people are control dependent on I3? They are control dependent on I3. Is this clear? Similarly, these people are also control dependent on I3. Is this clear? So basically, all I can say, when you have a branch instruction, then all the subsequent instructions, all the following instructions, they actually depend on this branch, right? They are depending on this branch. Everyone is looking at this branch. Okay, will I execute or not? Depends on this branch. Will I execute or not? Depends on this branch. So you can see that if you have a branch instruction, then all the following instructions, they are depending on this branch. So that is called control dependence. That these instructions are also control dependent on I3. These instructions are also control dependent on I3. This is what is given here. Okay, so you can notice if you have a branch instruction, this is your branch instruction. Branch if not equal. Branch if equal, right? This is your branch if equal. What this means? BEQ. What this BEQ means? This means branch if equal, jump if equal. And what this means? BNE. This means branch if not equal. Okay, so you can easily see that the point is very simple, that if you have a branch instruction, then whether to execute these instructions in the memory or whether to execute these instructions in the memory, we do not know. So that is called control dependence. This is called control dependence. So all the subsequent instructions, they are control dependence. This is called control dependence. I hope this point is clear. Anyway, so what are the solutions then? We have seen what are, did you understand that branches create a lot of problem? Do you agree? So far, whatever we have seen, do you agree that branches create a lot of problem? Because we don't even know where to go. We don't even know which next instruction to execute. Yes or no? Branches, they create a lot of problem. Let me tell you, in the pipeline, these are the real villain. Just like RAW hazards. Okay, RAW hazard, just like that, these branches are also real villain, because we don't know which instruction to execute. We don't even know which next instruction to fetch. Should we fetch the instruction which is just below it, or should we fetch the instruction from the target address? So basically, we don't know what to do. That is the reason branch instructions are very problematic. Did you understand the problem? So far, we have only seen the problem we have seen. I told you what is the problem that is happening because of branch instructions. The problem that is happening, that we have seen. Okay, understood? I'm not getting replies. Please tell me. Like, if you don't reply, then how will I know whether you are understanding or not? Okay. So now let's see. The next topic is solutions. Let's discuss the solutions. What are the solutions? One by one, we will see the solution. The first solution is this. Okay, this is the first solution. Just first solution, what is that? The first solution is that basically don't fetch anything until the branch target is resolved. Okay, solution one, what the solution one is, let me tell you. The solution one is very simple. This is extremely simple solution. Okay, this is extremely simple solution. What this solution means? This solution simply means that just don't fetch anything until you don't, until you know, until the branch target is resolved. Very intuitive solution, right? Yes or no? Isn't it very intuitive solution that basically, okay, see what I'm saying. Solution one, what is the solution one? Solution one is stop fetching. Solution one is stop fetching. Just stop fetching until the branch target is resolved. Now a very beautiful concept I'm going to tell you. Okay, see now what I'm going to tell you, please understand this. Okay, so just stop fetching until the branch target is resolved. Just stop fetching until you know the branch target. Now, so what is the solution actually? This solution simply say that this solution one, this solution one simply says that, it says that stop fetching. Okay, just stop fetching until we know the target address. Okay, until we know the target address, until we know the target address of the branch. Okay, just stop fetching. So this is what you do. Just stop fetching until we know the target address of the branch. Very simple solution, isn't it? Okay, isn't it very simple solution that just stop fetching until we know the target address of the branch. Now here there are actually two types. Let me tell you something I'm telling you. You just know, just see this. So there are two types. Stop fetching. Now stop fetching when we are saying that stop fetching. We are saying stop fetching. Now there are two solutions. Either you stop fetching until you know whether it is branch or not. Okay, see what I'm telling you. Okay, please understand this. Let me assume that you don't know this instruction. Okay, let me give you a real scenario, a real world scenario I'm giving you. Let me tell you, I know that what is this instruction, but you don't know what is this instruction. Okay, let's play a game. Are you ready? I am playing a game with you. Okay, you see this. I know what this instruction is, but you don't know. Okay, you are the instruction fetch stage. You are the instruction fetch stage, then there is instruction decode stage, then execute stage, then MA stage, and then write back stage. You are the, this is you. This is you. Okay, now you tell me. Now you tell me. This instruction I1 you are fetching. Okay, instruction I1 you are fetching. I1 is going here. In the next cycle, I1 is going here. In the next cycle, I1 is going here. Then I1 is going here. Then I1 is going here, and so on. Okay. Like for example, let's assume this is your cycle C1, cycle C2, cycle C3, cycle C4, cycle C5, something like that. Or maybe I can create, I can put like this. Just for a moment, let me create the diagram like this, that you have these stages. These are the stages. So you can see that this is your instruction IF, instruction phase. Then you decode, then you execute, use the ALU, then data memory access, and then write back. Okay, these are the cycles. Now let's play a game, a simple game we are playing. Cycle C1, 2, 3, 4, 5, 6, and so on. Now you tell me, this instruction I1, I'm not telling you what is this instruction. I did not tell you what is this instruction. Okay, so you will fetch it. You will do everything with it. I1, it will go away. Okay, you tell me, you tell me a simple point. Should I fetch the next instruction here? Should I fetch I2? A simple question I am asking. Should I fetch I2 in this cycle? In the cycle C2, should we fetch I2? A simple question I am asking. Tell me the answer. Should I fetch I2? Did you understand my question? My question, did you understand? That should we fetch I2? So you can see that by chance, if you fetch I2, by chance, if you fetch I2, let's assume that this is your solution. Let's assume your solution is yes. Let's assume you fetch. Assume you fetch. Okay, please understand. Assume we fetch. Then what is the problem? Tell me. Tell me then what is the problem? Assume we fetch. Assume we fetch. Then what is the problem? Tell me. What is the problem if we fetch? If you are fetching it, then tell me simple point. When will I know this I1 was branch instruction or not? When will I get to know this I1 was branch instruction or not? When will I get to know? I am getting to know. Okay, when will I know that this was branch instruction or not? Somewhere by the middle of C2, right? Yes or no? This is your cycle C2. This is your cycle C2. Okay, please understand. This is your cycle C2. This is the cycle C2. In the cycle C2, you will decode and you will read the register. Let me assume here you are reading the register, and let me assume here you are decoding. Let me assume. Okay, this is your cycle C2. In the cycle C2, let me assume you are decoding and then you are reading the register. Then you are reading the register, because in this cycle we read the register, right? Yes or no? We read the register. That you already agree with me. Okay, so let me assume that you decode here and you read the register. So at this point of time, we will know whether it is, at this point of time, we will know it is branch or not. This I1 is branch or not, correct? Agree? At this point of time, at this point of time, at this point of time, we will know I2 is branch or I1 is branch or not. I1 is branch or not. Okay, at this point of time, I will know whether it is branch or not. But before that, I2 we have already fetched. Yes or no? Before that, I2 we have already fetched. Agree? Before that, I2 we have already fetched. So what is the solution then? What is the solution then? Then what is the, basically the solution number one? I told you solution number one. What is the solution number one? The solution number one is never fetch the wrong instruction. Never fetch wrong instruction. Never fetch wrong instruction. Okay, never fetch wrong instruction. So this is what this solution is. Solution is saying that stop fetching until the branch is resolved. But you tell me, so what should I do then? What should I do then? Then this is the solution I need to do. After every instruction, I stop fetching, right? Yes or no? Do you agree with me that after every instruction, I have to stop fetching? Solution one, in the stop fetching, okay, either after every instruction, I stop fetching. Please see this. Please, did you understand this? That after every instruction, I stop fetching. Every, whether branch or not. Did you understand this solution? Let me know. Why I am stop fetching after every instruction? After every, let me tell you, every means even if it is addition instruction, subtraction instruction, okay, branch instruction, non-branch instruction, whatever instruction is this, okay, I am stopping fetching. I am stopping fetching after every instruction. Why? Tell me, please tell me why. Why I stop fetching after every instruction? Why I stop fetching? Because in the second stage, I will get to know if it is branch or not. Yes or no? Very good. Because we don't know if it is branch or not. When you are fetching it, okay, I am fetching it, I don't know it is branch or not. In the ID stage, in the second stage, I will find out it is branch or not. Is there any lagging in the video? In the audio video, are you facing any lagging? Okay. So tell me, understood this solution? After every instruction you fetch, you stop fetching. This is your solution one, that after every instruction, stop fetching. After every instruction, stop fetching until in ID stage, we get to know if the instruction is branch or not. Clear? Okay, clear? Is this clear? This is very bad, right? This solution is pure bad solution. Do you agree with me that this is the worst solution that can happen? Do you agree with me that this solution is the worst solution that can happen? Like after every instruction, after every instruction, you are stopping fetching. It simply means that in this solution one, in this solution one, okay, part one, you can notice this is worst solution. Why this is worst solution? Why this is worst solution? Why this is worst solution? This is worst solution because just think about it. If even if it is add instruction, I1, it is add instruction, then I2, then I3. If it is subtract instruction, if it is branch instruction, okay, whatever instruction you take, what will happen? I fetch this, I stop fetching. I fetch this, I stop fetching. I fetch this, I stop fetching. Okay, even the normal instructions are also taking how much time? Just think about it. Even the normal instructions are also taking how much time? I fetch it, I stop fetching. I fetch it, I stop fetching. I fetch it, I stop fetching. So you can notice your CPI, many stalls, many stalls, right? Many stalls are there, many stalls. Actually, after every instruction, there is a stall. After every instruction, one stall. After every instruction, at least one stall. At least one stall. Agree? This is the worst solution. Why this is the worst solution? Because after every instruction, one stall. Isn't it? Please tell me. What is the better? Something better can you do? Can you suggest me something better? Anyone? Can you suggest me something better? Something better. Sir, please do this. Sir, these are the villains. It's like this. These are the villains. Because of these villains, the normal people are also giving you stall. This person giving you stall. This person giving you stall. This is the actual villain. See, the actual villain is branch. This is the actual villain. But because of this actual villain, because of your solution, these normal people are also giving you stall. Is this clear? Like in your society, just think about it. In your society, there are some bad people. Because of those bad people, even the normal people, even the good people also, you are not trusting. Something like that. These branch people, these are the bad people of the society. Because of these bad people of the society, even the good people like addition people, subtraction people, these are the non-branch people. These are the good people. Even you are not trusting these good people. Even these good people are also giving you one stall. After every instruction, you are getting one stall. Can you give me some suggestion? Suggestion is, if you can know someone is good or not, yes or no? If you find out something is good or not, so basically the better solution in the solution one, the second version, what is the second version of the solution one? Stop fetching. In the stop fetching, this is the part two. What this is the possibility to what you do? Somehow in the IF stage, you find out IF stage has extra logic, has extra hardware, just to find out, just to find out branch or non-branch. Like in this stage, we just put extra hardware just to find out if instruction is branch or not. If instruction is branch instruction or not. Okay, are you getting my point? In the IF stage, we have some extra hardware just to find out if some instruction is branch instruction or not. Now what will happen? Tell me, with this solution, what will happen? Anyone? Now with this solution, what will happen? Now with this solution, what will happen? Let me tell you. So in the solution one, the second version of the solution one, now what will happen? Now this will happen that we will stop fetching after. Now in this solution, we will stop fetching when? After every instruction. Tell me, will we stop fetching after every instruction? No, we will stop fetching only after every branch instruction. Correct? Okay, clear? So we will stop fetching only after every branch instruction. Only after every branch instruction. I hope you understood. So in this solution, we have some extra hardware in the IF stage. In the instruction fetch stage, we put some extra hardware just to detect, just to find out whether the instruction is branch instruction or not. With this solution, the addition instruction will not give you an extra stall. The good people, the good instruction, the non-branch instruction, they will not give you extra stall. Okay, so we will stop fetching only after every branch instruction. So what we have seen, there are two solutions. One is stop fetching. So this is the stop fetching solution. Clear? The stop fetching solution. What the stop fetching solution has two types. What is the type one? Tell me. What is the type one and what is the type two? Tell me, please tell me. What is the type one? What is the type two? This stop fetching solution has two types. This has two types. The type one is stop fetching altogether. Very good. Okay. This is your, the type one is stop fetching after every instruction. After every instruction. Stop fetching after every instruction. What is the type two? Type two is stop fetching after every branch instruction. So who will find out if it is branch or not? If the instruction is branch or not? If the instruction is branch or not, who will find out? IF stage will have some extra logic. Okay. So for this type 2, we need some extra logic. We need some extra logic, some extra logic in IF stage. Correct? Okay. If you want to implement this solution, if you want to implement, then in the IF stage, some extra solution, some extra logic you need. Understood? Are these two solutions understood? Intuitively, can you tell me? Okay, let's discuss intuitively. We have seen what is control hazards. Okay, because of branch instruction, there are some problems happen. Yes or no? Branch instruction will create a lot of problem because we don't know what is the next instruction to execute. That is the problem these branch instructions will give you. If you have the branch instruction, you don't know what will be the next instruction to execute. You don't even know that. Okay, so these branch instructions, they are the real villain. They create a lot of problem. Now we are discussing the solution of branch hazards. The problem because of branch instructions, the problem that are happening, the bubbles that we are getting, the stalls that are created. Okay, so we want to resolve that. We want to find solutions of control hazards. Okay, now the first solution is that very intuitive solution. Do not do anything. Yes or no? The first solution is basically don't do anything. The first solution is saying don't do anything. Basically what is it is saying that stop fetching. Okay, the solution one is saying stop fetching. Now there are two types. You are stopping fetching. You are not going to fetch. But there are two types. Either you stop fetching after every instruction. Okay, after every instruction. If it is good instruction, bad instruction. If it is branch instruction, non-branch instruction, whatever instruction it is, you stop fetching after every instruction. Why we are doing that? Why we are stop fetching after every instruction? Because we don't know if the instruction is branch instruction or not, if the instruction is good instruction or not. Okay, so in the ID stage, we will find out if it is branch instruction or non-branch instruction. In the ID stage, we will find out if it is addition, multiplication, subtraction, branch instruction, what it is. Okay, in the ID stage, we will find out. So that is the reason we stop fetching after every instruction. But that is very bad. That is the worst solution that can happen. Okay, that is the worst solution that can happen. Why? Because of bad people, because of branch instruction, you stop trusting the good people. You stop trusting the non-branch instructions. Basically, every instruction is giving you at least one stall. Yes or no? Every instruction is giving you at least one stall. Every instruction is giving you. That is the worst thing that can happen. So that is the worst solution that can happen. So what is a better solution? One step better. One step better. So what are the steps? What is the better solution? The better solution is that in the IF stage, in the fetching stage, you put some extra hardware, some extra facility, functionality. Okay, so that you can find out where in the IF stage, you can find out if it is good person or bad person. In the IF stage, when you are fetching the instruction, you can find out if it is branch instruction or non-branch instruction. Okay, very simple. If it is non-branch instruction, then you fetch the next instruction. there is no problem. If it is non-branch instruction, then you just keep fetching, there is no problem. But if it is branch instruction, then you stop fetching until you find out the target address. If it is branch instruction, then you stop fetching until the target address is known. These are your solution one, stop fetching solution. Did you understand stop fetching solution? Please tell me. The first solution, stop fetching solution. Did you understand type 1, type 2? Did you understand type 1, type 2? Tell me. Stop fetching solution, type 1, type 2. Did you understand that? Understood? Okay. Very simple, right? Okay. So now let's move on. So you can see that this is your solution. So by default, which we use type 1 or type 2? By default, which we use type 1 or type 2? By default, which we use, this type 2 is the by default. Okay. This type 2, this is the by default stop fetching solution. This is the by default stop fetching solution. Okay. So very simple. Now in this, basically in the stop, basically the conclusion is this. This is the conclusion. This is the conclusion. Solution 1. This is the solution 1. Okay. So the solution 1 is basically stop fetching after every branch instruction. Stop fetching after every branch instruction. Okay. Is this clear? Stop fetching after every branch instruction. Until when? Tell me. Until when? Until target address is known. Until target address is known. Okay. Until target address is known. Very simple. This is your solution. Now let's move on. So in this solution, basically we are putting the bubbles, because you are stop fetching. It means you are putting the bubbles, correct? Okay. So basically in this solution, if you have a branch instruction, let's assume you have a branch instruction, some branch instruction you have. Branch if not equal R1, R2. Okay. Go to some, and you have your 5-stage pipeline. Your 5-stage pipeline. Let me assume that in execution stage, means that is your 3rd stage, correct? So let me assume that in execution stage, branch is resolved. Branch is resolved. Okay. Let me assume that in the execution stage, branch is resolved. Branch is resolved. Okay. So let me assume this. Let me assume that in the 3rd stage. So what will happen? Tell me then. Then because of this instruction, what will happen? When you fetch this instruction C1, C2, C3, C4, C5, and so on. So when you fetch this instruction I1, instruction ID, execute, MA, WB, when you fetch this instruction, this is your branch instruction. Okay. So when you fetch this, then in the next 2 cycles, what will happen? Tell me, in the next cycle, what will happen? In this cycle C2, what you will fetch? Nothing. Bubble. Okay. So you can notice bubble 1. This is your bubble 1. Because this is a branch instruction. I told you that after every branch instruction, after every branch instruction, after every branch instruction. Okay. After every branch instruction. So please understand that, because this is a branch instruction. So after this branch instruction, we stop fetching. Okay. Until the branch is resolved. So there will be 2 bubbles. Bubble B2, 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 B2. So there will be 2 bubbles. Okay. KS is asking why to bubble in all stages. No. KS, bubble is not something like, it's not like, this is just a terminology. Bubble is not something like in your pipeline, some bubbles are happening. Okay. It's not like that. Okay. This bubble simply means that in this stage, you are not fetching anything. Bubble simply means that in this cycle, you are not fetching anything. In this cycle, you are not fetching anything. Are you getting my point? In this cycle, you are not fetching anything. In this cycle, you are not fetching anything. Okay, that is your bubble. That is your two stalls. Because what is a perfect pipeline? Case. What is a perfect execution? Perfect execution means, okay, perfect execution means in every cycle, new instruction you are fetching. In every cycle, one instruction is completing. Okay. In every cycle, one instruction is completing, one instruction completing, one instruction completing. But here you can notice that in the cycle C2, new instruction is not coming. In the cycle C3, new instruction is not coming. What it means? It means that in every cycle, one instruction is not completing. Okay. So you can notice these are called stalls. Bubble means stalls. Now let's move on. So you can easily see that if the branch is resolved, if the branch is resolved only in the execution stage, then two unwanted guests, then two extra stalls will be there. Let's move on. What is another solution then? This solution that we have seen, stop fetching solution we have seen, solution 1 we have seen, right? Now let's see the solution 2. What is the solution 2? That is static branch prediction. Okay, that is static branch prediction. So what this solution says, let me tell you. This solution, what this says, in the last solution, in the solution 1, what we were doing? In the solution 1, what we were doing? Please tell me. Please tell me. In the solution 1, what we were doing? We were stopping fetching. Yes or no? We were stop fetching. Okay, after every branch instruction. Right? This is what we were doing, correct? After every branch instruction. Until target address is known. Until target address is known. Okay, this is what we were doing. What is the solution 2? Solution 2 is saying that, why stop fetching? Right? Why stop fetching? Because sometimes the instruction that you are fetching, that may be useful, right? See, the solution 2 is saying, why every time stop fetching? Why after every branch? Why after every branch stop fetching? Why after every branch stop fetching? The solution 2 is saying that why after every branch, like after every branch you are stopping fetching, that is not good. What the solution 2 is saying, for example, let me assume that your instruction is this. This can happen, right? Tell me, this can happen, right? Branch if equal. If these people are equal, then go to label. But it is possible that they are not equal. Assume they are not equal. Then what will happen? Tell me. Assume R1 is not equal to R2. Then tell me what instruction will be executed. This instruction I5 will be executed or label should be executed. Tell me which instruction should be executed. Tell me. Assume R1 is not equal to R2. So what instruction should be executed? So this is the correct flow. This is the correct execution. The correct execution will be I4, then I5. This is the correct execution. So can you see that why you are stopping fetching? Let's fetch. If there is problem, then flush. Do you agree with me? Do you agree with this solution? This solution is smart solution. This solution is smart. So what this solution 2 is saying, tell me. What this solution 2 is saying? This solution 2 is saying that keep fetching. Keep fetching. If any problem, we will flush. Keep fetching. If any problem, we flush. If any problem, we will flush. So tell me, in the solution 1, after every branch instruction, 2 stalls are coming. Do you agree? In the solution 1, after every branch instruction, 2 stalls are coming. But in this solution, after some branch instruction, stalls will come, right? Yes or no? Because if any problem, then you will stall. If any problem, then you will stall. Then you will flush. Is this clear? Let me know. In the solution 2, if there is any problem, you will stall. You will flush. If there is no problem, then no problem. So this is the difference between solution 1 and solution 2. What is that? Solution 1 versus solution 2. Here you are stopping fetching. and here you are keep fetching flush if problem, flush if any problem. So tell me which solution is better? Tell me which solution is better here? Which solution is better? Let me know. Which of these solution is better? This is a better solution. This solution is better. This solution is better actually. The reason is very simple, because here after every branch, instruction 2 stalls. After every branch instruction, you are getting 2 stalls. And here you will get 2 stalls after some branch instructions. Here, after some branch instructions, you will get 2 stalls. After some branch instruction, you will get 2 stalls. So please understand that here after some branch instruction. So this is definitely better solution. Now there are 2 actually. Now, so tell me, if you have a branch instruction, there are 2 type of solution. 2 is basically static prediction. This solution 2, the name is static prediction. This is the name. You are doing static prediction. So 2 type of static prediction you can give. Either you can do this type of static prediction, or you can do this type of static prediction. What this static prediction is, let's assume this is a branch instruction. This is some branch instruction, let me assume. Okay. Then you can notice this I2, this is called fall through path, right? This is called fall through path. What is this called? This is called fall through path. Okay. And so another is, let's assume some IK. This is your taken path. Clear? Is this clear? This is some taken path. Taken path means if you are jumping, this is called taken path. And this is called fall through path, because this is, you are just falling. You are just going in the sequence. Okay. Now you tell me, there are 2 type of static prediction. What is that? The prediction 1 is static prediction. Either you can do this prediction. What prediction you can do? You can do this prediction that's just to take it. Okay. Because this is static prediction, so you cannot use your brain, right? Do you agree? This is static prediction. So you have to just decide one and for all. You have to decide that what to do. So this is the prediction you are making, that just don't take. Okay. So you are making this prediction that not taken. Not taken means, so what you will do? Tell me. So after this branch instruction, you will execute this instruction. Okay. Is this clear? You will execute this instruction. If you will flush, of course, you will flush. If there is any problem, you will flush. But what you are doing basically, after every branch instruction, you are executing the next instructions in the fall through path. After every branch instruction, you are just assuming that branch will not be taken. Every time you are assuming, every time, for every branch instruction, you are assuming that the branch will not be taken. So basically, this is what you are doing. This is your prediction. Every time, this is your static prediction. Is this clear? This is your static prediction. And if your prediction is wrong, then what you will do? This is your static prediction, that it will not be taken. It will not be taken. Branch will not be taken. This is your prediction. So if this prediction is wrong, then what you will do? If your prediction is wrong, in the execute stage, you find out your prediction is wrong. In the execute stage, you find out you should go to IK. You find out you should go to IK. Then what you will do? Then you will flush. Yes or no? Then you will flush. If any problem, then flush. If any problem, then flush. So this is your static prediction not taken. Another prediction is what? Another possible prediction is what? Tell me. Another prediction is what? That is taken. You are doing this prediction that it will be taken. You are making this prediction that it will be taken. You are making this prediction every time. For every branch instruction, you are making this prediction that it will be taken. It will be taken. This is your prediction. This is your prediction. Tell me, in this prediction, tell me, if you find out in the execution stage, in the third stage, you find out that actually you should not go here, you should go here. Then what you will do? In the execution stage, you find out that you should not go to IK. You should not jump. You should not jump. You should go to I2. Then what you will do? Then you will flush. Then again you will flush. So if prediction fails, simple point, if prediction fails, then what happens? If prediction fails, then flush. Then flush. So if prediction fails, then flush. And how many stalls? And how many stalls? Tell me, how many stalls? And K minus 1 stalls. Branch resolved in kth stage. If branch resolved in kth stage. So if prediction fails, then flush, and K minus 1 stalls. These are your solutions. So there are two types of solutions. One solution is branch predict not taken. Every time you just say, okay, it will not be taken, it will not be taken, it will not be taken. Another solution is every time you say it will be taken, it will be taken, it will be taken. Is this understood? See what this predict taken is. Okay, let me explain what this predict taken is. This predict taken scheme. What this scheme is, let me tell you. This scheme simply says that, okay, this scheme assume that this is actually, you can always assume this point, you can always assume that in the IF stage, you know that it is branch or not. Okay, is this clear? IF stage knows branch or not, knows instruction is branch or not, instruction is branch or not. Okay, this you can always assume, that IF stage knows that instruction is branch or not. This you can always, this is your, like this you can by default assume. This you can by default assume. You can assume this by default that IF stage knows that if it is branch or not. Okay, now you can notice this, what this predict scheme, what this scheme says. This scheme says that for every branch instruction, we assume it will be taken. We assume it will always be taken. It will always go to target address. It will always go to target address. Like without checking, it will always go to target address. Okay, are you getting my point? It will always jump. Basically, it will always jump. I can say it will always go to taken path. It will always go to taken path. Clear? Just assume, we just assume that it will always jump. Means this is what we are assuming in this scheme. So in this scheme, what we do, if you have this I1, if this instruction is your branch instruction, let me assume, if this is the branch instruction, then what will happen? Then this is a fall through path. Okay, this is your I1, I2. This is what is this path? Tell me, what is this path? This path is called fall through path. This path is called fall through path. And this path, IK plus 1 and so on. This path is taken. This path is called taken path. Okay. So in this scheme, what we do, whenever you have a branch instruction, then we just assume that it will always be taken. Are you getting my point? Whenever you have a branch instruction, we assume that it will always be taken. This scheme is called predict taken. Of course, if you want to implement this, then what do you need to do? If you want to implement this case, if you want to implement this, then what you will have to do? In the IF stage, some extra logic you will have to put. Is this clear? Case, if you want to implement this scheme, if you want to implement this predict taken scheme, if you want to implement, then in the IF stage, you will have to put more hardware so that you can also find out the target address. See, the IF stage can find out if it is branch or not. You will also have to put extra logics, extra hardware. If it is branch, what is the target? It immediately tells you the target. See, it will not do any calculation. Please understand. Please understand. You are thinking that IF stage will do any calculation. No. IF stage is not doing any calculation. IF stage is dumb stage. It is just telling you this is the label. See, this is the IK, this is the label, but you have to check whether it is equal or not. Are you getting my point? See what I'm telling you. Without checking, please understand. Now, please understand this predict taken scheme. What this scheme says, predict taken scheme is like this. Please understand. This is the scheme that if your instruction I1 is like this, branch if equal, branch if equal. If these two people are equal, then go to label. Okay. If these two people are equal, then go to label. Then you have I2, then you have I3, and there is label. Okay. Now you tell me what this scheme does. This predict taken scheme, what this scheme does? This scheme simply goes to label. It does not check R1 or R2. In this scheme, basically, just go to label. Sorry, what is that? Okay, so what I'm saying, just go to label. Just go to label without checking R1 equal to R2. Are you getting my point? Is this clear? Let me know. Without checking R1, R2, without checking R1, R2, from this instruction, just go to this instruction. Means you are just assuming in your mind, you are just assuming that it will most probably be taken. In your mind, you are assuming that most probably they will be equal. Most probably they will be equal. So just go there. Clear? These two schemes, are they clear? Which is more easy to implement? Which is more easy to implement? Of course, predict not taken. This predict not taken, this we do not have to do anything. This is the easiest to implement, right? Yes or no? This is the easiest to implement because that is by default. That will always happen if you do not put extra logic, if you do not put extra hardware, if you do not put extra brain, then that will always happen. This is easiest to implement because anyway we will face the next instruction, right? Yes or no? Agree? This is a very easy to implement because anyway, if it is a branch instruction, anyway we will face I2, anyway we will face I3, no problem. So you don't have to do anything. This is easiest to implement. This predict not taken. In the predict not taken, we are just assuming that this is your predict not taken. Clear? Now we will do some questions, but tell me, is this clear? You can read about predict taken, predict not taken. Here you can read. Let me read it for you. Okay, please read this. Please read this. See, predict not taken. What this predict not taken? Read this, what I'm telling you. Predict not taken, the hardware assumes that the next instruction to be executed will be the instruction following the branch instruction in the main memory. Clear? Is this clear? That predict not taken, the hardware will assume that the next instruction to be executed is the instruction that will follow the branch instruction in the main memory. And in the predict taken, what we do? In the predict taken, we assume that we will jump. Okay. And if there is any problem, you will flush. If there is any problem, you will flush. You will flush from the hardware. That's it. Now we will see some questions. With questions, all the concepts will clear. But tell me, at this point of time, are they clear? The solutions that we have seen for the branches, are they clear? Predict taken solution, predict not taken solution. These are static solutions. These are static dumb solutions. These all are dumb solutions. We are not using this. Are you getting my point? We are not using this. These are static solutions. Okay. Static solutions means you don't have to use this. You are just saying that, okay, branch instruction is there. Most probably it will go to the next instruction in the main memory. In the main memory, if the branch instruction is there, then most probably it will go to the next instruction. What this solution is called? What this assumption is called? in the main memory, the branch instruction, the next instruction will be the next instruction in the main memory. What this assumption is called? This assumption is called predict not taken, right? Yes or no? Is this clear? This assumption is called predict not taken. What I'm saying, please see this. This is your main memory. This is the main memory. In the main memory, this is your branch instruction. This is your fall through path. And let's assume this is your label. So you can see that this is your branch instruction. Your branch instruction is something like, if they are equal, if R1, R2 are equal, then go to label. So this label is here. Okay. This is your I1, this is your I2, this is your I3, and so on. So you can notice that what predict taken says, predict taken, what predict taken, where it will go? Where predict taken will go? Tell me. This is where predict taken. This is your predict taken. Predict taken, this is your predict taken scheme. This type of scheme is called predict taken scheme. And what is this scheme? What is this scheme? What is this scheme? This is your predict not taken scheme. Okay. Now let's see some questions, some beautiful questions. Let's solve. Take your copy pen. Please take your copy pen. Let's solve some good questions, some good quality questions. Let's solve. So let's assume that this is your question and some other details are given to you. You have a 5-stage classical pipeline. Okay. Let's assume that in EX stage, branch is resolved. Let's assume branch is resolved. In the EX stage, branch is resolved. Okay. Let me assume I am giving you this. You have the classical 5-stage pipeline. Your classical 5-stage pipeline you have. The question is asking what is the CPI? The question is asking CPI. You have a classical 5-stage pipeline. Okay. I am giving you this information that branch is resolved in 3rd stage. In the 3rd stage. In the execution stage. Execution stage means that is your 3rd stage. Okay. So that is your 3rd stage. Okay. And let's assume that this is your solution. What is your solution? Let's assume this is your solution. The solution is stop fetching after every branch instruction. So let's do the practice of that. Are you getting my point? Let's do the practice of that. Means stop fetching, just stop fetching. Just stop fetching after every branch instruction. This solution we have seen, agree? This solution we have seen, stop fetching after every branch instruction. So as soon as you know that, as soon as you see in the IF stage, this you can implement when this solution stop fetching after every branch instruction. After every branch instruction you stop fetching, not after every instruction. Okay. Addition instruction, subtraction instruction, after those you don't stop fetch. You stop fetching after every branch instruction. If you want to implement this solution, what do you need? Some extra functionality in the IF stage. Yes or no? In the IF stage, some extra facility, some extra hardware in the IF stage. Okay, this is your solution. Now you tell me about the CPI. Now you tell me about the CPI. What will be the CPI? CPI means CPI. That means clock cycles per instruction. That means cycles per instruction. So now you tell me what is the cycle per instruction? What will be the cycle per instruction? 20% instructions are branch instructions. The question is saying 20% instructions are branch instructions. 50% of branch instructions are taken. 50% of branch instructions are taken. This information, does it help us? In this solution, do we care about taken or not? Array, tell me, in this solution, do we care about taken or not? In this solution, do we care about this or not? Array, in this solution, do we care about taken or not? Do you care about taken or not? In this solution, stop fetching after every branch instruction. Stop fetching after branch instruction. This information is useless, irrelevant. अरे क्वेश्चन में कोई इंफॉर्मेशन दिया तो इसका मतलब ये नहीं है कि उसको यूज करना है. दिस इंफॉर्मेशन इज irrelevant because this is your solution. For this solution, this information is irrelevant. Clear? Is this clear? Because you are stopping fetching after every branch instruction. So please understand this point. Our solution was this. Understand our solution. Our solution is just stop fetching. This is our solution. Stop fetching after every branch instruction. Okay, clear? Stop fetching after every branch instruction until target is resolved. Until branch is resolved. So we don't care about taken or not. So in this solution, if you notice, in this solution, we don't care about taken or not. We don't care about taken or not. Okay. So your answer will be what? See, your ideal CPI is what? Array, think about per instruction. Always think about per instruction. If you want to find CPI, think about per instruction. Think in terms of per instruction. Think in terms of per instruction. Think in terms of per instruction. Okay. In terms of one instruction, we will think. Think in terms of per instruction. So tell me, if per instruction I am checking, now I will check per instruction, I will check. When everything, like when there is no branch instruction, when your everything is perfect, then one will be taken. Array, one cycle will be taken, right? When everything is perfect, one cycle will be taken by every instruction. Right. By every instruction, one cycle will be taken. One cycle will always be taken. This is the ideal situation. This is the ideal CPI. It will always happen. One cycle will always be taken by every instruction. This is the ideal CPI. This is the ideal situation. Now you tell me, in one instruction, like per instruction, how many instructions are branch instruction? See, 25%, 20% of all instructions are branch. Then for one instruction, how many are branch? Okay, so you can notice that the question is saying that 20% of all instructions are branch. 20% of all instructions are branch instructions. This is what the information is saying. So from this per instruction, how many branch instruction? From this per instruction, how many branch instruction? Per instruction, how many branch instructions? Tell me. From this per instruction, how many branch instruction? That will be 0.20. 0.20 per instruction, these many branch instructions. Right? Yes or no? 0.20. Because that will be, I can say 20 divided by 100. So you can see that 0.20 per instruction, these many branch instruction. So you can notice for every instruction, let's look at per instruction. Per instruction, ideally we will take one cycle. This is what will happen ideally. But per instruction, these many branch instructions are there. Per instruction, these many branch instruction. Because of one branch instruction, how many stalls? Because of one branch instruction, how many stalls? 2 stalls because of one branch instruction. 2 stalls per branch instruction. Because in the third stage, because in the third stage, this branch is resolved. Because in third stage, branch resolved. So in the third stage, branch is resolved. That is the reason. In third stage, branch resolved. That is the reason 2 cycles. 2 stalls. So your final answer will be what? So tell me per instruction, how many cycles? Tell me per instruction, what is the number of cycles? That will be 1 plus 0.20 multiplied by 2, that is 1.4. This is your answer. Understood? Understood? Let me know. Did you understand? So we have seen the practice. We have done the practice of first solution. Our first solution practice. This is basically your first solution practice. Okay. First solution, solution 1 practice. This is your solution 1 practice. Okay. Let's see the solution 2 practice. Now let's see the solution 2 practice. Again, the same situation. Branch resolve where? Branch resolve in third stage. Let's assume branch resolve in third stage. You want to find the CPI, and let me assume that this is the solution you are using. What is the solution? Your solution is predict not taken. Predict not taken. This is the solution you are using. Okay, you are using this solution, predict not taken. In this solution, what will happen? You are having this solution, predict not taken. This predict not taken solution, can I write like this? Just tell me a simple point. This predict not taken solution, another way of writing this solution is this. Can I say in the predict not taken, we stop fetching. Can I say that this solution is same as this solution? We stop fetching after taken branches. Right? Yes or no? Do you agree with me? Do you agree with me that this is equal? This is same as after taken branches, bubbles will be there. Yes or no? Array, basically after taken branches, bubbles will be there. For taken branches, bubbles will be there. What will happen? For taken branches, bubbles will be there. Stalls will be there. Correct or not? Is this clear? Let me know. This predict taken, like this I can say. Can I say like this? The predict not taken, can I say like this? That predict not taken, that is same as for taken branches, bubbles will be there. Because you are predicting that it will not be taken. This is your prediction. Your prediction is this. This is the prediction. This is the prediction. So when prediction is wrong, here the prediction fails. Here the prediction fails. So when the prediction fails, then stalls will be there. Okay. Understood? Because your prediction is not taken. This is your prediction that it will not be taken, not be taken, not be taken. But if you have taken branches, means your prediction is failing. If your prediction is failing, then stalls will be there. Then bubbles will be there. Then you will have to flush. So after the taken branches, you will have the stalls. For taken branches, you will have the stalls. Now you tell me the answer. 20% are the branch instructions and 50% are taken. 50% of branch instructions are taken. 50% of branch instructions are taken. So now your CPI will be what? Now your CPI will be like this. So you can notice that per instruction, 1 cycle will be taken. This will always happen. This is the ideal situation. This is the ideal CPI. Ideally, this will happen that 1 cycle will be taken by everyone. Everyone will take 1 cycle. Every instruction will take 1 cycle. This is the ideal situation. But per instruction, how many branch instructions? Per instruction, how many branch instructions? These many branch instructions per instruction. These are the branch instructions per instruction. These are the branch instructions per instruction. So this is the number of branch instruction per instruction. In these branch instructions, 0.50 times stalls will happen. These are the taken branches. These are the taken branches. When you have taken branches, then 2 stalls. 2 stalls for every taken branch. For every taken branch. So you can notice for every taken branch, two stalls will give you. You can notice these are the total number of branches per instruction. These are the total number of branches. Among these branches, these are the taken branches. Then you will have two stalls for every taken branch. So your answer is what? Your answer is 1.2. Your answer is 1.2. So for this question, the answer will be 1.2. Understood? Let me know. Ankit, Alap, KS, understood? Is this clear? Very simple, right? Now let's see the next question. What about this question? Tell me the answer. Can you solve this and tell me the answer? Control dependence quiz. 25% of all instructions are taken branches. The question is telling you that 25% of all instructions are taken branches. You have a 10-stage pipeline. Correct target will for branch computed in the 6th stage. The 6th stage will give you. Everything else is smooth. What is the actual CPI? Tell me, if 6th stage is giving you, then what is the number of stalls? What is the number of stalls? Number of stalls will be 5. Number of stalls will be 5. But you can notice that this is your quiz, that 25% of all instructions are taken branches. You have 10-stage pipeline. Correct target address will be computed. Let's assume you are using this solution. I did not mention the solution, right? I did not mention the solution. Did I mention the solution? What is the solution? So let me assume the solution is this. Solution is predict not taken. Let's assume the solution is predict not taken. So if your solution is predict not taken, then your answer will be what? So your answer will be what if your solution is this? If your solution is predict not taken. And your answer will be what if your solution is predict taken? In these two situations, your answer, you tell me. If your prediction is this, predict not taken. In this situation, your answer will be what? In this situation, your CPI will be 1, which is ideal CPI. This is the ideal. Every instruction will take 1 cycle. Every instruction, ideally, it will take 1 cycle plus. Okay, 1 cycle plus. You can notice that 25% instructions are the actually. So this information is not for us. Actually, to solve this question, information is not given. To solve this question, the information is not given. But the simple for this question, the information is given. For this question, what I'm saying, predict taken. For this solution, information is not given. The question has not given you the information. So basically, the question is assuming this predict not taken. So now you tell me the answer. Predict not taken is your scheme. So your scheme is, let me tell you, like your solution is your scheme. Predict not taken scheme you are using. So let's assume you are using predict not taken scheme. This scheme you are using, predict not taken scheme you are using. And this is by default also, let me tell you, because this is easy to implement, right? This is your by default scheme also. Okay, because this is very easy to implement, predict not taken. This is very natural because you will always bring the next instruction. You are anyway bringing the next instruction. So this is your ideal CPI. Every instruction will take 1 cycle. But you can notice that these many are the taken branches per instruction. These are the taken branches per instruction. Per instruction, these are the taken branches. Okay, and everything is giving you 5 stalls. Okay, 5 stalls per taken branch. Per taken branch. Whenever you are taking a branch, you need to pay the penalty, right? Why you are paying the penalty for taken branch? Why we are paying the penalty for taken branch? Why not for the remaining branches? For not taken branches, why we are not paying the penalty? Why we are paying the penalty for taken branches? Because your solution is predict not taken. Your solution is this. Is this clear? Array, for the taken branches, Only for the taken branches we are paying the penalty. Why? Because your solution was not taken, your prediction was not taken. So this is your prediction, your bet was not taken, but ultimately it was taken. Because it was taken, so your prediction was wrong. So that is the reason you have to flush, the instruction that you have taken, that you have brought in the pipeline. Okay, so you can notice here your answer will be this one. You can calculate what is this one, tell me. That is 1.75. This is your CPI, this is your answer. Okay, let's move on. Let's see this gate question. This is a beautiful question. Let's solve this. Let's solve the first part. Let's focus on the first part only. Let's focus on the part A. Then we will focus on the part B. But first you focus on the part A. Okay, read the question carefully and tell me each and every point. Why some information is given, why some information is not given. For example, this is a GATE 2000 question. You have an instruction pipeline. There is an instruction pipeline which has 5 stages. Each stage is taking 2 nanoseconds. Okay, so your cycle time is given to you, right? Cycle time is given to you 2 nanoseconds. Each stage is taking 2 nanoseconds. Every stage is taking 2 nanoseconds. So cycle time is given to you 2 nanoseconds. All instructions use all the 5 stages. Every instruction. Okay, for this question, the answer will be, for this question, the answer will be 2.25. For the previous question, answer will be 2.25. Okay, anyway, now let's come back to this question, this gate question. There are 5 stages. You have an instruction pipeline which has 5 stages. Each stage is taking 2 nanoseconds. It means your cycle time is given to you because every stage is taking 2 nanoseconds. Every stage is completing its work in 2 nanoseconds. Okay, every stage it is completing its work within 2 nanoseconds. So that is your cycle time. All instructions use all the 5 stages. What this means? All instructions use all the 5 stages. What this means? All instructions use all the 5. This is your in order pipeline. Okay, this is just simple your in order pipeline, that every instruction will go through all the stages. Every instruction will go through all the stages. This is your normal in order pipeline. Okay, branch instructions are not overlapped. What this means? This means that, please read this and tell me what solution is this. The instruction after the branch instruction is not fetched until branch instruction is completed. The instruction after the branch instruction is not fetched. What solution is this? Tell me. What solution is this? The instruction after the branch instruction is not fetched. What solution is this? The instruction after the branch instruction is not fetched. Okay, the instruction after the branch instruction is not fetched. No. Case, read this. Instruction after the branch instruction is not fetched. This is your solution 1 type 2. This is your solution 1 type 2, because the question is saying that the instruction after the branch instruction, please see this, the instruction after the branch instruction, read this. The instruction after the branch is not fetched till the branch instruction is completed. Till the branch instruction is completed. So tell me, when the branch target will be resolved? When the branch target will be resolved? Tell me, what is the number of stalls then? What is the number of stalls then? Till the branch instruction is completed. The question is saying till the branch instruction is completed, like the branch instruction will go to IEF, then it will go to ID, execute, memory access, then finally it will go to WB. Okay, so the number of stalls will be 4, right? Yes or no? Until the branch instruction is completed, means your branch instruction will be completed. It's like this. Let's assume this is your branch instruction. Your branch instruction is IF, then so in the cycle C1, 2, 3, 4, 5, 6, and so on. Here you are going to IF, then you are going to ID, then you are going to execute, then you are going to MA, then you are going to write back. Okay. Now here the branch instruction will be computed. Now here you can face the next instruction. Okay. So you can face the next instruction here. So what this question is saying, until the branch instruction is completed, the branch instruction will be completed here. Here the branch instruction will be completed. Here the branch instruction is completed. In the next cycle, you can face the instruction. Okay. So you can notice this is a bubble. This is a bubble. Here you cannot. How many bubbles? One bubble, two bubble, three bubble, four bubble. Is this clear? Understood, Alap? Is this clear? Visualization. Is the visualization clear? Four bubbles we got. Right? Yes or no? Four bubbles we got because you cannot see. See, this is your branch instruction. This is your branch instruction. So it's like this. This is your branch instruction. Now I2 you cannot fetch. In the next cycle, in this cycle, there will be bubble. So there is a bubble. This is your bubble B1. In this cycle also, there will be a bubble. There will be a bubble. In this cycle also, there will be a bubble. There will be a bubble. In this cycle also, there will be a bubble. But finally, here you will fetch. Yes or no? But finally, here you will be able to fetch. Okay, here you will be able to fetch I2. Correct? Your whatever is this instruction. Here the next, whatever is the correct, this is the correct next instruction. This is the correct next instruction. If the branch is taken or not. So this is the next correct instruction. So that you will fetch here. So how many bubbles are there? Alap, 4 or 5. How many bubbles? Did you understand visualization? Please tell me. Is the visualization clear? Is this visualization clear that you are getting only 4 bubbles? Okay, you will only get 4 bubbles. Is this clear? Because the question is saying that the branch instruction is completed. Until the branch instruction is completed, till the branch instruction is completed, here the branch instruction will complete, here it will complete. So in the next cycle, you can fetch. So 4 bubbles you are getting. So you can easily see that you are getting total 4 bubbles. 4 bubbles. So number of stalls that you are getting, that is 4. Okay. Because you can always calculate like this. Instruction is completed. So your branch is resolved in the last stage. You can understand like this. Branch instruction is completed. It means in the last stage, in the 5th stage, your branch is resolved in the 5th stage. So now you tell me the answer for this question. Now the question is saying average instruction execution time. Calculate average instruction execution time, assuming that 20% of all instruction are branch instruction. Okay. So in this solution, do we care about taken or not? In this solution, do we care about taken or not? Do we care about taken or not? We don't care about taken or not. Okay. So your answer will be what? So your CPI will be what? Ideally, this will always happen. This is the ideal CPI. Every instruction will take 1 cycle. Okay. So every instruction is going to take 1 cycle. But how many branch instruction per instruction? Tell me how many branch instruction per instruction? Tell me how many number of branch instruction per instruction? How many? How many branch instructions per instruction? That is 20%. So that is 0.20. These many branch instruction per instruction. This is the number of branch instruction per instruction. Okay. For everything, for every of these 4 cycles. So your answer is what? CPI. Your answer is a 1.8. This is the cycles per instruction. This is the cycles per instruction. But what the question is asking? Is the question asking 1.8? Is the question asking cycles? Is the question asking cycles or time, execution time? What the question is asking? The question is asking execution time, remember. Please understand, average execution time. So what that will be? So your final answer will be what? So remember, your CPI is 1.8, but your final answer will be what? Final answer, that is your average execution time. That will be what? That will be 1.2 multiplied by 2 nanosecond. That is the cycle time. This is the cycle time. So your answer will be 3.6 nanosecond. This will be your answer. Okay. Very simple. Now let's see this question. The second one. The second part. Let's solve the second part. Now forget about the first part. Now forget about the first part. Just forget about it. Now you tell me the answer for the second part. What the second part is saying? If a branch instruction is conditional branch, if a branch instruction is conditional branch, branch need not be taken. If a branch is not taken, the following instruction can be fetched. The following instruction can be overlapped. Okay. When 80% of all branch instructions are conditional branch instructions, okay, when 80% of all branch instructions are conditional branch instruction and 50% of 50% of okay, I think we also need to use this information. Actually, you also this is subjective question, I think. Anyway, this information also we need to use, that these many instructions are branch instruction, that 20% are the branch instruction. Okay, this information also we need to use. Now the question is very simple. Now the question is very simple, that now focus on this. Tell me what solution is this in the option B. What solution we are using? Can you tell me? Read the option B and tell me what solution you are using. What solution you are using in this option B? What solution you are using? See this, the solution that we are using, that if the branch is not taken, then the following instruction can be overlapped. Following instruction you can overlap. This is your branch predict no, yeah, okay. So this is your predict not taken. This is your solution predict not taken, correct? Yes or no? Your solution is predict not taken, because in this solution, you keep fetching the instructions. And if there is any problem, you flush them. Okay, so this is your solution here, predict not taken. What the question is saying? The question is saying that there are 20% branch instructions. Total, there are 20% branch instructions. In these 20% branch instructions, what the question is saying? In these 20% branch instructions, there are, in these 80% are conditional branches. So it means what? It means 20% are unconditional branches. Okay, unconditional branches, correct? Agree? 20% are unconditional branches. Okay, and the question is saying that in these branches, in these conditional branches, okay, the question is saying that in these conditional branches, 50% are taken. In these conditional branches, 50% are taken and 50% are not taken. 50% are not taken, 50% are taken. You tell me where your solution, your prediction is this, and this is your prediction, because the question is simply saying that if branch is not taken, the following instruction you can overlap. If the branch is not taken, the following instruction you can overlap. The following instruction you can bring. If the branch is not taken, the following instruction you can bring. So this is your prediction. Your prediction is not taken. This is your prediction. Tell me here. So do we need any? How many stalls we need here? Just tell me, simple point I am asking. How many stalls we need here? 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 0. There is no stall. There is no extra stall. Okay, because your solution is not taken. Your prediction is not taken. This is your prediction. You are doing this prediction that it will not be taken, and it is not taken. Your prediction is same. Okay, you are making this prediction. You are making this prediction that it will not be taken, and it is not taken. So the number of stalls will be 0. Here, what will be the number of stalls? Here, what will be number of stalls? Because your prediction is not taken. This is your prediction. Your prediction is not taken, not taken, not taken. Your prediction is not taken. So that is failed here, because unconditional branches will always be taken. So here your number of stalls will be what? That number of stalls will be 4. And here your number of stalls will be what? That also will be 4, right? Okay, that also will be 4, because number of stalls will be 4. So your final answer will be what? Tell me, your CPI will be what? Your CPI will be 1. 1 is the ideal CPI. Ideally, this is the ideal CPI. It will always happen. Every instruction will take 1. Okay. Now per instruction, how many branch instructions? Per instruction, these many branch instructions. Please understand. These are the per instruction branch instruction. 20% branch instruction per instruction. 20%. Okay. So these many branch instruction per instruction. In this 20%, 80% are 80% times. So basically, actually, if you want to solve this question, let me tell you, you can make 3 paths. Okay, just calculate this path, and calculate this path. Okay, there are 3 paths. So please understand this. If you want to solve this, you can solve this path. Let's call it P1. You can solve this path. Okay, you can solve this path. You can solve. Let's call it P2. And you can solve this path. Let's call it P3. So you can notice that here what will happen? 20% are the branch instruction. In these 20%, 80% are conditional branches, 80% are conditional branches. In these conditional branches, 50% will give you 4 stalls. Plus. These are the branch instructions. In these branch instructions, 80% are unconditional conditional branches. In these, 50% will give you 0 stall. So actually there is nothing to calculate. This is just 0. So this path you don't have to calculate, right? This path you do not have to calculate because this will give you 0 stalls. Plus 20% branch instructions, 20% unconditional, and they will give you 4 stalls. So what is the final answer? Can you tell me? Can anyone tell me what is the final answer then? Can you calculate? Can you calculate this and tell me the final answer? What is the final answer? Tell me. Take your calculator, or can you do this? Like very easily you can do this. Tell me the answer. Anyone? Or you have to just find this value. This value you just have to calculate. Okay, so this is anyway 0. This is anyway 0. You can remove this because this is anyway 0. What is this one? This is your 4. So 0.4, 4 multiplied by 0.4. So that is 1.6. This is your 1.6. Okay. This is 1.6. And what is this? What is this one? Okay, so you can just check it out. Okay, so this is 0.16. Huh? Okay, anyway, so let's see. Divided by 100. So that will be 0.16. Okay. So that is 0.16. And what is this value? What is this one? This one. What is this one? This is 0.32. Total, what is this? So total, what is the total CPI? That will be 1.48. So your final answer will be what? Your CPI is 1.48. Your CPI is 1.48, but the question is asking what? The question is asking execution time. Average execution time. Okay, the question is asking average execution time. That will be 1.48 multiplied by 2 nanosecond. This will be 2.96. 2.96 nanosecond. Okay, this is your answer. Clear? So these are simple questions. I hope you are understanding all these questions. Are you understanding? Now let's see this question. There is again a 5-stage pipeline. This is GATE 2006 question. 5-stage pipeline, 1 gigahertz frequency. That means 1 nanosecond is the cycle time. Okay, 1 nanosecond is the cycle time. You have a cycle time of 1 nanosecond. That is your cycle time. Instruction fetch happens in the first stage of the pipeline. A conditional branch instruction computes the target address and evaluates the condition in the third stage of the pipeline. Okay, third stage. So tell me, what is the number of stalls? Like if there is any problem, then what will be the number of stalls? That will be 2. Okay, because the question is saying that a conditional branch instruction executes the target address, evaluates the condition in the third stage of the pipeline. The processor stops fetching new instruction following a conditional branch. Okay, the processor stops fetching new instruction following a conditional branch. What solution is this? What solution is this? This is your solution. What solution is this? This is solution 1 type 2. Solution 1 type 2, right? Okay, because we are stopping fetching. We stop fetching. The processor stops fetching new instruction. The processor stops fetching new instruction following a conditional branch. After a conditional branch, you stop fetching until the branch is known. A program executes 10 power 9 instruction, out of which 20% are conditional branches. If each instruction takes 1 cycle to complete, see what the information, look at this information. If each instruction takes 1 cycle to complete on average, the total execution time. Okay, the question is saying very simple. The question is saying that there are 10 power 9 instructions. There are these many instructions. Out of these many instructions, how many conditional instructions? How many conditional branch instructions? Out of these many, how many conditional branch instructions? The question is saying that 20% are conditional branch instructions. So 10 to the power 9 multiplied by 20 divided by 100. These many conditional branch instructions we have. Okay. Now you can easily see what is the execution time. The execution time will be what? So average execution time. First you find out average CPI. Or maybe you can just find out average execution time. What the question is saying that each instruction is taking 1 cycle to complete on average. Please see this line. Please see this line. Each instruction on average, each instruction is taking 1 cycle to complete. So for these many instructions, how much time? For these many, 1 nanosecond plus, right? Because this is given to you. This is given to you that each instruction on average, this information is given to you in the question that each instruction on average takes 1 cycle. Okay, each instruction takes 1 cycle to complete. This information is given in the question that each instruction on average takes 1 cycle to complete. So 10 to the power 9, these many instructions will take this much time, plus some extra time will be taken by whom? Some extra time will be taken by whom? Tell me. Some extra time will be taken by whom? These conditional branch instructions. So these many conditional branch instructions you have, and because of them, we need 2 more, these many extra cycles. Actually, I can say these are the extra cycles. This is the extra time. This is the extra time this multiplied by 1 nanosecond. You will also have to multiply with 1 nanosecond. This is the extra time. So finally, your answer is what? Is this point clear? That basically, because of these conditional branch instruction, these many are the conditional branch instruction. So because of these conditional branch instruction, how many extra cycles? Extra cycles will be 10 to the power 9 divided by these multiplied by 2. These many extra cycles. Okay, this is the number of extra cycles. These many. So what is the extra time? Extra time you multiply with 1 nanosecond. Your final answer will be what? This is 1 nanosecond. Nano means 10 to the power 9 minus 9. So you can notice your final answer will be what? Average execution time, that is equal to 1 plus, okay, because anyway 10 to the power 9, 10 to the power minus 9, they will cancel out. So your final answer will be this 1 second plus 1 second. Only second will be remaining. Only second will be remaining. 1 second plus this nano and this will cancel out. These two will cancel out. Nano and 10 to the power 9. So your answer will be from here 0.4 seconds. So your answer will be 1.4 seconds. Your answer will be in seconds. So the answer is going to be 1.4 seconds. The answer will be option C. Okay. So easily you can do all these questions. Are you comfortable with all the questions? All these questions, are you comfortable? Okay, one final topic, one last topic, just some more questions we will solve. There is solution 3. What is that? Solution 3 is dynamic branch prediction. Okay, dynamic branch prediction. It is like machine learning. Okay, this solution is very much like machine learning or artificial intelligence. This solution is similar to like machine learning. Okay, from the data you are keep learning, you keep changing your prediction. Is this clear? This solution, dynamic branch prediction, this dynamic branch prediction, you keep getting new information you keep getting, and you keep changing your prediction, you keep changing the prediction. This is called dynamic branch prediction. How this is implemented, that is not I can say needed for us. Even in the books it is not given. Okay, even in the books also the implementation is not given. How to do this by dynamic branch prediction, how to implement this, the implementation, how can we do this dynamic branch prediction, that is not required for us. Even in most of the books also, in most of the standard books also, that is not given to you. So we will not see how this is done. Okay, how this is done we will not see. But in the GATE exam, the question will come based on the performance. In the GATE exam, if any question comes from this dynamic branch prediction, if any question comes, then that will come based on performance. So that question we will see. Okay, so let's assume there is a dynamic branch predictor. Let's assume, just assume in your mind, you assume that there is a predictor, and this predictor, what this does, it takes new information, it keeps getting new information, and it keeps changing its prediction. Okay, so let's assume that there is a dynamic predictor. You have a predictor in your hardware. Okay, who can do the branch prediction? Let's assume. Now let's solve this question. This is our last question, and with this our chapter will be over. So let's solve this question. Tell me the answer. You know what is CPI, right? We have seen so far this formula. We have seen in case of control hazard, what is the CPI? In case of control hazards, how do we find CPI? How do we find CPI? We find CPI by 1 plus something like that. Yes or no? This will be ideal. This is how we find CPI. In case of control hazards, the CPI will be 1 plus. How many mispredictions you are doing per instruction? How many mispredictions you are doing? How many mispredictions you are doing per instruction? Means how many problems are happening per instruction? How many mispredictions? What is the number of mispredictions you are doing per instruction? Number of mispredictions per instruction. Okay, multiplied by what? Multiplied by number of stalls per mispredictions. Number of stalls per misprediction. Correct? Yes or no? Is this clear? Please tell me. This is how we have found out. Yes or no? So far we are using basically this formula. I did not tell you the formula. We were using our normal intuition, our logic, normal logic we were using, but this is the formula. Is this formula clear to everyone? Many questions we have solved using this formula so far. Without using this formula, we are using this formula. So basically, how to find the CPI? That is 1 plus. How many mispredictions are happening per instruction? In one instruction, how many mispredictions you are making? And because of one misprediction, how many CPI, how many stalls you are there? Okay, that's it. This is your formula. Now you tell me the answer here. Let's assume 20% of all instructions are branch instruction. 20% of all instructions are branch instructions. And this, you have to calculate this. You have to find this, you have to find this, you have to find this, you have to find this. Tell me, quickly tell me the answer. There is a branch predictor. There is a branch predictor. Let's assume there is a branch predictor. And this is the branch predictor accuracy. This accuracy is the branch predictor accuracy of branch predictor. So let's assume in your hardware, you have a branch predictor. In your hardware, you have a predictor. This predictor you have in your hardware, branch predictor. So this, what this accuracy is given, this is the given for branch predictor. Remember, this accuracy is given for branch predictor. So there is a branch predictor. We are using a branch predictor who will do the prediction. Okay. And this predictor has this accuracy, 50% for branch instructions and 100% for all the remaining instructions. Branch you are resolving in the third stage. Then tell me what is the CPI? Tell me what will be the CPI? CPI will be 1 plus, what should I write? Tell me what should I write? 1 plus. Remember accuracy, 50% for the branch instructions means for 50% instruction, there is no extra stall, right? Agree? Do you agree? It's like there is a predictor, there is a Baba, there is a, there is some, I can say some wizard is there. Okay, let's assume that there is some predictor, there is some wizard, and this wizard can calculate 50% of the time you don't have to, you will not have any extra stalls. 50% of time it is accurate. It is accurate. 50% it is accuracy. It has accuracy. It means 50% of the time it will never give you any stalls because of branch instruction. So the answer will be CPI will be 1 plus the remaining, okay, 1 plus these many branch instructions you have. These are the number of branch instruction per instruction multiplied by per branch instruction these many wrong predictions. These are the wrong predictions. These are the mispredictions, right? Per instruction. Do you agree? Do you agree that this is the misprediction per instruction? Look at this. This is the mispredictions per instruction. This is the mispredictions per instruction. Okay, per instruction we are making these many misprediction per instruction because in one instruction these many branch instructions we have. Okay, please see these many branch instructions we have, and for these many wrong predictions we have. So these are the number of mispredictions per instruction multiplied by 2 because these many stalls will be there. So this is your answer for this case. For this case, what will be the answer? What will be the equation? Tell me. 1 plus these many branch instructions. You have these many branch instructions, but 90% are accurate. So the remaining will give you the 90% are accurate. So the remaining are the misprediction. 90% accuracy. 90% is the accuracy. So for the remaining, you will get 2 stalls. For the remaining, you are getting 2 stalls. Clear? What about this one? Only this data is changing. So instead of this 2, you are using what? Very simple. Instead of this 2, just use 9. Similarly, instead of this 2, just use 9. That's it. This is your answer. Correct? Is this clear? Now let me ask you another question. What is that? In this, what is the speed up? Like 2 questions I am asking you. For example, you forget about this one. You forget about this one. You forget about this one. You tell me, what is the speed up if we go from here to here? Which is better? First of all, you tell me which is better. Which solution is better? Is this better or this better? The top one is better or the first one is better? Which of them is better? Among these 2, which is better? Which is better predictor? Which is better system, I can say? Which is better pipeline? Tell me, which is better pipeline in these 2? If you calculate, the second pipeline will be better because what is this value? Can you calculate? What is this value? What this will come out? This will come out to be 1.2. And this will come out to be what? And what this will come out to be? $1.04, right? This will come out to be 1.04. So you tell me which is better. So you can definitely see that second, the lower solution. Okay. So you can notice the lower solution, the lower one. The lower one is better. Okay. What the speed up then? The lower one is better, but what is the speed up? What is the speed up then? Now you tell me the speed up. Over above upper one. What is the speed up of lower one up above? So that will be your 1.2 divided by 1.04. What is that? You can calculate. Whatever is that you can calculate. 1.15. Very good. Okay, so that will be 1.15. Okay, so like this type of question also they can ask. They can ask you what is the speed up of using this on this, this on this. Like they can ask you anything. See, they can ask you what is the speed up if we use this over this? What is the speed up if we use this over this? This type of questions they can ask you. Okay, understood? Basically, what questions they can ask you? They can ask you any question. Like if you use this system, we use this system, then which system is better? If we use this system and also use this system, which system is better? And what is the speed up? So this type of questions they can ask you. I hope all these points are clear. So this is your chapter. This is your control hazards. We have seen everything. So please tell me, understood? Did you understand everything? A simple thing is remaining. That is very final point is remaining. That is your one last solution. Okay, one final solution is remaining. That is delayed branch. Okay, that is delayed branch. So let me just quickly tell you. That is one simple solution. Okay, delayed branch. This is last solution, the final solution. I can say solution number 4. So let me quickly discuss that also. The solution 4. And this solution is called delayed branching. Delayed branching. This is actually very popular solution because this is done in the RISC pipeline. In your MIPS, in your classical stage pipeline, this is the solution used. Delayed branching. Okay. Let me tell you why this is popular. Why? What is the reason this is popular? This is actually used in our classical 5-stage pipeline, 5-stage MIPS pipeline. Okay, RISC pipeline, MIPS, or you can call it RISC pipeline. So in that pipeline, actually, this solution is used. This delayed branching solution is used. This solution is like this. What this solution says, let me tell you what this solution says. Let's assume that in ID stage, everything is resolved. Assume in ID stage, branch is resolved. Then what it will mean? Branch resolved. Then how many stalls basically? Tell me. Assume in ID stage, branch resolved. Then what is the number of stalls because of misprediction? Due to some misprediction, tell me. What are the number of stalls because of misprediction? That will be 1. Because in the ID stage, in the second stage, this is the second stage. So that is the reason the number of stalls will be 1. Okay, very simple. Now you can see one thing. Just tell me a simple solution. This is very intuitive solution. You tell me whether it is branch, whether it is conditional or not. Okay, this is a branch instruction. Whether it is conditional or not. Do you agree that one instruction will be fetched? Yes or no? Because one unwanted guest will come in your pipeline. Okay, then you will have to flush it. Right? Yes or no? Agree that one unwanted guest will come. This I2, okay, then this I3, and maybe this is your IK. Now, I don't know whether I should go here or whether I should go here. Okay, either this or this. Either this or this. See, either this or this. One of them is correct. Next instruction. Do you agree? One of them is is correct next instruction. But we don't know. But in IF, we don't know. But in the IF stage, we don't know. Correct? Yes or no? In the instruction fetch stage, we don't know. In the IF stage, we don't know which of them is correct. One of them is correct. One of them is correct, but in the IF stage, we don't know. Now, of course, there are problems. There are problems in the C1, C2, C3, C4. For example, if you face the instruction, which is a branch instruction, if this is a branch instruction, okay, you fetch it, you decode it. But when you are decoding it, at that point, already who will have come? Already one of those instructions will come. Yes or no? Agree? Already I2 will come. We don't know whether it is correct or not. One of them is correct, but we don't know which of them is correct. Okay. One of them is correct, but we don't know which of them is correct. Now you tell me a simple question I am asking. One of them is correct next instruction, but which is correct next instruction? I don't know. So should I execute I2 after I1 in the pipeline? After I1, should I execute I2? Yes or no? In the pipeline, should I execute I2? One of them is the correct next instruction. So you tell me, in the pipeline after I1, should I execute I2? No, right? That can create problem. That can create problem. Should I execute IK? Tell me, should I execute IK in the pipeline after I1? Should I fetch IK? In the pipeline after I1, should I fetch IK? Answer is no. Should I fetch I2? Answer is no. I cannot fetch I2. I cannot fetch IK. Then what to do? This delayed branching, what it says, let me tell you, it says that because you know that one stall is possible, so this is called delay slot. Okay, means there is one delay slot. Is this clear? Because if you have misprediction, because of misprediction, if by chance there is some misprediction, okay, you are bringing some instruction will come in the pipeline after the branch instruction. This is your branch instruction. After the branch instruction, one instruction will come in the pipeline. Only one unwanted guest can come, right? That is called delay slot. So what is delay slot? Let me tell you. Delay slot means how many unwanted instructions can come in pipeline. Okay. Delay slot means, what is delay slot? See, if branch resolves in kth stage, then how many delay slot will be there? Tell me, please tell me. Quickly tell me. If branch resolves in kth stage, then how many delay slots? Then there will be k-1 delay slots. Very good. Okay. So then k-1 delay slots. You have k-1 delay slots. Okay. So there will, if the branch is resolving in the kth stage, then there will be k-1 delay slots. Now, what this delayed branch is saying? This delayed branch is saying that this is delayed branch. Let me tell you the delayed branch concept. So this is your branch instruction. If it is successful, then tell me if this is pass. If this condition is pass, then where it will go. And if this condition is fail, then where it will go. If this fails, it will go to fall through path. Correct? Do you agree? If the condition fails, then it will go to fall through path. This is some conditional branch instruction. Okay, this is some conditional branch instruction. So tell me, if this is your conditional branch instruction, if the condition fails, it will go to fall through path. And if the condition passes, then where on which path it will go? It will go to taken path. Correct? Are yes or no? If the branch instructs, if this is your conditional branch instruction, this is a conditional branch instruction. If the condition fails, then it will go to fall through path. And if the condition passes, it will go to taken path. Okay. It's like this. This is your I instruction. This is your branch instruction. Let's assume this is the condition. This is a conditional branch instruction. This is a conditional branch instruction. BEQ R1, R2 label. So tell me, what is the fall through path and what is this is your I2, this is I3, and this is label. Which is taken path and which is fall through path? Tell me, please tell me. If the condition fails, where you will go? Tell me. In the condition fails, where you will go? If this condition fails, if this condition fails, if this condition fails, where you will go? If the condition fails, you will go here. If the condition fails, you will go to I2. And if the condition passes, you will go here. If the condition pass. So I told you that this is your taken path. I told you this is your taken path. And I told you this is your fall through path. Okay, what this delayed branching says? This delayed branching says that, okay, let me tell you what this delayed branching, see, this is interesting. This is really interesting. What this delayed branching says. This delayed branch scheme, what this says? This scheme says that if you have a branch instruction, okay, if I1 is branch instruction, if this I1 is branch instruction, then what this delayed branching instruction, this is very smart scheme. What this says, it says that if this I1 is branch instruction, then what you do, and number of delay slot is 1, right? Number of delay slot is 1, correct? If your number of delay slot is 1, number of delay slot, that is 1. Okay, so you can notice that if you have a branch instruction, then what you do, here you put some other instruction. Basically, the compiler will do this. Who will do this? Compiler will put some independent instruction will be put here. Some independent instruction will be put here. Okay, by compiler. By compiler. Remember, this is your delay slot, correct? Because there is only one delay slot. So that is the reason. Why the only one delay slot? Tell me. Why we have only one delay slot? What is the reason we have only one delay slot? Because in the second stage, we are resolving the, yes or no? We are resolving in the second stage. In our classical RISC pipeline, in our MIPS pipeline, we are resolving in the second stage. In the ID stage, we are resolving the branch. So that is the reason only one unwanted guest can come. Okay, only one unwanted guest can come in the pipeline. So you have only one delay slot. This is your delay slot. So what this delayed branching says, this says that in this delay slot, the compiler will put some instruction. The compiler will put some independent instruction. So where your fall through path is there, actually your fall through path will be here, I2, I3. Tuk, 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 tuk. This is your fall through path. So remember, your fall through path is here. So your fall through path is shifted. Can I say? Can I say your fall through path has shifted? Your fall through path has shifted. And similarly, this label, and this is your taken path. This is your taken path. And some independent instruction we are putting. Now you tell me. Okay, please. Now you tell me. Just think about it. Whether branch, now is there any problem if this happens? Like if this happens, is there any problem? If you fetch I1, okay, is there any problem? Tell me. C1, C2, C3, C4, and so on. Now, when this branch instruction, when this is here in the decode stage, and you fetch this independent instruction, you fetch this independent instruction you fetch. Is there any problem? No problem, right? Independent instruction we are putting, the compiler has put independent instruction. The compiler has put some independent instruction. So now there is no problem. You can execute it. Okay, now at this point of time, you will know what is the correct instruction. Then, okay, after executing this, then you can either go to fall through path, or you can go to this taken path. Is this clear? What I'm saying? I am saying the very simple point I'm telling you. This is the branch instruction. The compiler will choose a suitable instruction. The compiler is going to choose a suitable instruction, and that instruction will be put in the delay slot. Okay. Is this clear? KS is asking independent to condition. Yes. Independent means this is some suitable instruction. This instruction is some suitable instruction which does not affect anything, which does not affect. For example, maybe this instruction is some instruction just before branch instruction. Maybe that instruction you are putting here. Okay. Maybe this instruction which is in the branch, which is before the branch instruction, maybe that instruction you are putting here. So that this instruction does not affect anything, even if it execute. This is what I'm saying. Even independent means, what independent means? It means that even if this instruction executes, you know that either this should be executed or this should be executed after the branch, right? Case, is this clear what I'm saying? You know that after the branch instruction, either I2 should be executed or label should be executed. Either the fall through instruction should be executed, sorry, the first instruction of fall through path should be executed, or the first instruction of taken path should be executed. Do you agree with me? Case, after the branch instruction, either the first instruction of fall through path should be executed or the first instruction of taken path should be executed. But what compiler has done, this compiler has put one independent instruction which does not affect anything. Even if it executes, even if you execute this independent instruction, then also it does not affect anything. It does not affect the branch. If it does not affect the program, it does not affect the correctness of the program. Is this understood what I mean by independent instruction? Independent instruction means even if I execute this, then the correctness of the program does not get affected. Okay, is this clear? Case. So this is the idea that now you tell me whether the branch is taken or not. Whether in this scheme, whether the branch is taken or not, who will be executed? Whether the branch is taken or not, who will be executed? Can I say who will be executed? This instruction will be executed, which the compiler has put in the main memory after the instruction. Okay, this compiler will put this compiler. Remember, this compiler has put this instruction in the main memory after the branch instruction. So this will be executed. Okay, in the main memory, this is your main memory, and this is what compiler has done. This is your branch, and this is your delay slot. In the delay slot, one independent instruction has been put, some instruction has been put. Okay, and this is your fall through path. Remember, please understand that this is your fall through path. This is your fall through path. So can I say the first instruction of fall through path will be executed? Can I say? Can I say the first instruction of fall through path will be executed? Can I say the first instruction of fall through path will be executed? Can I say? After the branch instruction, can I say the first instruction of fall through path will be executed? No. This instruction will be executed. Please understand. Okay, and this is your taken path. So whatever happens, whatever happens, branch is taken or not, this instruction will be executed. Is this clear? Whether the branch is taken or not, whether the branch is taken or not, this instruction executed. This instruction, which is next to branch instruction in main memory, is executed. Whether branch is taken or not. Whether branch is taken or not. Okay, clear? If the compiler cannot find out suitable instruction, then what it will do? If compiler cannot find out, this is a question. If compiler cannot find out suitable instruction, if compiler cannot find out suitable instruction, then what to do? Cannot find out suitable instruction. Suitable instruction to put in delay slot. Then it will put NOP instruction. Okay. If the compiler cannot find out suitable instruction to put in the delay slot, then it puts NOP instruction. Is this clear? Is this clear to everyone? Then it will put NOP instruction. How many delay slots are there? What is the number of delay slots? How many delay slots are there? Tell me. How many delay slots? Let me know. That is k minus 1. Okay, that is k minus 1, where k is the kth stage in which branch is resolved. This K, what is this K? This K is stage in which branch is resolved. If number of delay slots increase, then is it easy or hard for compiler to fill the delay slot with suitable instruction? If number of delay slots increase, if number of delay slots increase, then for compiler, is it easy or hard to fill delay slot, to fill delay slots with suitable instruction? With suitable instruction, the answer will be harder. Okay, the answer will be harder. So if the delay slots are increasing, you will have to find more instruction to fill the right? Yes or no? Are to fill the delay slots, you need more instruction. If the number of delay slots will increase, if let's assume there are 3 delay slots, if you have 3 delay slot, then the compiler needs to find 3 instruction, 3 suitable instruction. It will have to find out to fill those delay slot. That is very hard. Okay. So this is your delayed branching. Please tell me, did you understand this delayed branching? Let me know. Let me know. If anyone has any doubt, you can ask. KS is asking, can we use static and dynamic for the same architecture? Yeah, these things can be done. KS, practically all these things are done. Okay. Practically many complicated schemes are done. We have just seen the theoretical concepts. Is this clear? These are the theoretical concepts that we have seen. Practically, these will be used in a mixed fashion. Okay, practically some branch predictor will be used. Okay, so like all the type of things will be done practically. Like for example, your scheduling algorithms. In the scheduling in operating system, you study first come first serve. Okay, first in first out, SJF, round robin. Okay, so practically mixture of them is used. Okay, is this clear? So practically all these things are used. Any doubt? This is your complete explanation of control hazards, data hazards, structural hazard, many gate questions we have seen. There is not a single topic which I have missed. There is not a single thing in the pipeline I have missed. Complete pipeline we have seen. Okay. All the type of questions we have seen. Please tell me, did you understand? Let me know. Alap is saying that dynamic branch prediction is completely done in the hardware. Yeah, dynamic branch prediction, there is a hardware. It is called predictor. If you want, you can study that. I can provide you the lectures, but it is not required for the, I can say, gate exam. Also, it is not required for the undergraduate, I can say, computer organization course. As I told you, dynamic branch prediction, that is very complicated. I can provide you the lectures. If you watch the lectures, in 1 or 2 lectures, you will just skip and you will say, oh no, this is not for me. In ISC, you can study. You go to IIT, ISC, there you take the computer organization course. There you will implement. Okay. In those courses, you will implement these things. The prediction, the branch predictor, you will create the branch predictor. Okay. So all those things you will do. Practically you will do. Once you go to IIT, ISC Bangalore, this top institute, if you go, then you will do these things. So anyway, whatever we have seen, that covers everything that can be asked in the gate exam, that has ever been asked in the gate exam. This is everything in the Hamacher. You know, there is a book called Hamacher for computer organization. In that, in the pipeline lecture, whatever is there, we have seen that. In the pipeline lecture, super scalar system also I told you. You know, super scalar system means multiple instructions are using the same stage in the same cycle. In the same cycle, in the same stage, there are multiple instructions. That is super scalar system. I told you in order execution, out of order execution. Okay, RAW dependency versus hazard, data hazard, control hazard, structural hazard, all the type of gate questions. Okay, everything we have seen. This is your completion of, this is the completion of pipeline. Please tell me, did you understand this? Let me know. Any doubt in anything? Did you understand control hazard, data hazard? Are you confident in pipeline? Like, frankly, honestly, you tell me. Honestly, you tell me. Because we can have one back-to-back practice session we can have. See, concepts are covered. I have covered each and every concept. Now, if you want, we can have one practice session, back to back practice, all the gate questions, every question that from the standard resources, the Go classes test series question, the Go classes mock test question, gate overflow mock test questions. Basically, if you want, we can do that practice if you want. But what I'm telling you, to solve those questions, whatever concept you need to know, that concept we have seen. We have covered every concept you need for any gate question. Okay, for any Go classes test series question, for any gate overflow test series question, all those questions we have seen, all those concepts we have covered. I hope you understood. Okay, so let me know, should we have another session, one session only for practice? Like, should we have, or like, will you do it on your own? Will you do it on your own? This is my suggestion. What to do, just solve the gate questions, because gate exam is very near. Okay, gate exam is very near, so just solve the gate questions. Previous year gate questions, today you try. Gate or for PDF you open, in the Go PDF, go to pipeline and solve all the questions. Each and every question you solve. Is this clear? Each and every question you try, each and every question you solve. That is enough, because you have seen every concept. Okay, so thank you everyone. If anyone has any doubt, you can ask. Mavith has joined very late, but Mavith, you can watch the session as recorded. Okay, this recorded session you can watch. But what I'm telling you, everything we have covered, everything in the pipeline from starting till the end, everything we have covered, every concept, every variation, every question, everything. So just go through all the lectures. I have provided the annotated notes. You can check it out on the Go classes website in the computer organization course. At the bottom, in the end, you will find all the annotated notes. Also, you will find just solve all the gate questions. Each and every gate PYQ you solve. Okay. Okay. Thank you, everyone. Thank you so much. Our pipeline is over. Okay.